Hey everyone, my name's Madhav. So I've been studying machine learning for the past 5 years, and one of the best summaries I've found of the entire field has just been this one XKCD comic, which I know you can read, but just so I have something to do. This is your machine learning system. Yep, you pour the data into this big pile of linear algebra and then collect the answers on the other side. Now, there are a few ways to respond to this comic. The pedantic way is to say, yeah, no, there's also calculus in the pile, so it's wrong. The more sensible response just to say, I wonder what I've been spending the last 5 years of my life on. Though there is this new response I just learned about from these weird people called RL scientists, and their response just to say, hey, what if we added statistics to the pile? Well, that's how you get reinforcement learning. Anyways, RL is this kind of odd outlier field in all of AI because it is very different compared to most of the techniques that you interact with day to day. With that being said, it's really important. It's being used all over robotics and to improve chatbots that by now are probably using every single week. So, over the past 4 months, I've been diving into it. I used Richard Sutton's textbook and OpenAI spinning up RL docs, which are good, but they are really daunting in terms of the sheer amount of math that you have to wade into. So my goal today is to present a more minimal math intro to reinforcement learning. Minimal as in you don't have unnecessary math, but you do still have a bunch of math. What I'm going to do is I'll start by talking about some basic concepts, vocab, some equations, then dive into some older techniques, around the 90s, etc., which lead up to modern RL methods, including PPO, which is used all over the industry today. Now, I should warn you, by the time we get to around here, we're just going to be doing math all of the time. So this can be challenging. Some prereqs are first year university calculus, first year university programming, and it would be nice if you had some kind of probability course. I will give you a little bit of background, but you still need to ChatGPT and you still might be confused at times, though, you're welcome to follow along. So with those disclaimers out of the way, I'm going to get started with the first section on RL jargon. PS, if you ever want to skip forward, there's chapters. If you want to leave, take a break, come back, do so at any time. You'll find all of the chapters in the description. So let's get started. Let's talk about some key vocab we need to know for RL. The first keyword that I want to get you guys to think about is RL is entirely about trial and error. That's the name of the game with RL. With most areas of machine learning, we have supervised algorithms. Supervised means we tell the algorithms, here is the right answer. We know it's the right answer, you just got to get to it. With RL, it's different. We don't know what the right answer is, and we have to learn by trying different actions and seeing, oh, this one's better, that one's worse. As a concrete example, think about the way that you learn to walk, right? Your parents didn't hand you a manual to be like, move your lower muscle in your left leg. You just tried it out, you fell over, and over time, you figured out how to do it. This is what RL is like. This natural kind of learning that happens early in our life. What most of the other AI algorithms are like, in terms of quantity of AI algorithms, most are supervised learning, which is like studying for exams. It's like, let's say you have a math test to study for, and you get a worksheet where it's like, here are the right answers. You just figure out however you want to solve the question so you can get to the given right answers. So hopefully that helps you, especially this analogy, helps you think about which types of problems you need RL for. We need it in cases where we don't know what the right answer is. We don't have some solution to give to most other AI algorithms. So with that being defined generally, let's look into a few subcomponents, a few keywords that we'll keep talking about. The RL loop kind of combines all of the different components we need to learn about. So we have first an agent. An agent is like our algorithm. It's what we define to solve the problem at hand, like let's say figuring out how we learn to walk. Of course, the agent is in some environment, like let's say we have a robot learning to walk and it's in some room, right? Now, the agent, it can first of all create some outputs. Our algorithm can output things like, let's say, telling robot motors to move forward or back, and we call these outputs actions. So the agent, when it selects an action to perform, it might change something about the environment. And we measure those changes to the environment with states. So the states are the inputs to the agent. So again, with this robot walking example, our state might be, for example, our X, Y, and Z coordinates in the room, right? What is our position in the room? Alongside the states, so our current measurement of what the environment looks like, the environment also sends the agent some rewards, which are, thumbs up, thumbs down, whatever, things that tell the agent, are you doing good in terms of what you're trying? Is your trial and error going well or is it not? So for instance, we might have an agent, so some kind of algorithm that is controlling a robot that we want to be able to jump. So we might say, as the engineers designing the system, we might say, okay, we want high rewards when the robot has, a good height off the ground. If the robot is going higher off the ground, we will give you more reward. If you're close to the ground, you haven't figured out how to jump, we will give you less reward. Hopefully that example helps you tie together the main components of RL algorithms. With those jargon definitions out of the way, let's now look more into the agent. How does it, select these actions, and what does it do with the state and reward, the information about the environment that it's getting in? The first thing to define is what is the goal of the RL agent. Its goal is to learn which actions that it should take in each state, such that it can maximize the reward it's getting over time, right? It needs to learn how to use this information about the environment as it is to control the actions that it's outputting in such a way as to maximize its reward. Now, I know that sounds, like fancy words. You'll get used to it over time. Let me give you a couple of examples. So here's one example of an RL agent which is trying to navigate a maze. So these X's are walls that, the RL agent can't go through, and it's trying to get from the bottom left to its destination in the bottom right. So in this context, the actions are, left, right, up, down movements that the agent can do. The state might be which block of the maze that it's in, the X and Y coordinates in the maze. And the rewards can be, for example, let's say you get +1 if you get to the end and -1 if you don't. Here's another example that might help. So let's say you're an RL agent controlling this robotic cart. You have some motors that you can control that allow you to move the cart left and right. On top of the cart, you have this pole and a ball that is attached to the end of the pole. So now, this is obviously unstable. The pole wants to fall over. It doesn't want to stay upright. So we could have an RL agent that is trying to keep the pole upright by moving the cart. In this context, we can have, for example, actions being move left and move right. The state can be, for instance, what is the position of the cart? What is the angle of this pole? So is it upright? Is it starting to fall down? And finally, the rewards can be, for instance, you get +1 for every moment that we check in and the pole is still upright. Hopefully that gives you, some more practical examples of what the goal can be for different RL agents. If it's just, maximizing the total reward, well, we can define the reward such that we can give it the domain-specific goals of, let's say, reaching the end of the maze or keeping this pole, upright. Now that we have the goals defined, let's consider some other aspects such as how does the agent determine which actions to select? How does it determine what states and actions are good or not? So the way that RL agents do that is with value functions. Value functions can be in terms of state value, where they figure out for the agent how good it is to be in some states, or they can be as action values, where the agent is figuring out how good is it to take one particular action in some states. As some examples to define this, let's consider this grid world. So this particular position, that can be one state, and that can have, a high value because it's right next to the end goal of the agent, which is to get to this square over here. In contrast, the starting state, that has probably low value because it's very far from the goal of the agent. So the value functions can tell us or tell the RL agent which states to work towards such that it can get high rewards. In contrast, the action values, so those were the state values, the action values tell the agent things like, hey, if you're in that last square right next to the goal, probably a good idea to move right. Moving right has the highest action value compared to moving down or moving left, because those will not get you towards the goal. So you can, I guess, intuit why these value functions might be good things for the agent to know, or and somehow find a way to compute, because they will help tell the agent which states to work towards or which actions to pick in each state. Now, how do we compute these things? Well, for now, I will just keep it vague. I'll just say, the state value, we somehow have to figure out how much reward we can expect in some states. And likewise for the action value, how much reward we can expect from taking some particular action in some states. We'll define these mathematically in the next chapter. So let's say we now have this agent where we have defined the goal. So we've set some rewards and we've set these value functions. Now what? Well, the last part is we need to control the actions of some agent. So the actions of an agent are determined by policies. There are two types of policies. One is a stochastic policy, and the other is a deterministic policy. So a stochastic policy is just a function that returns the probability of picking some action in some state. Now this is read as, pi of a given s. This represents the probability of choosing action A given we're in state S. The reason why we call it stochastic is because we're outputting a probability, right? It's not guaranteed that we're going to take some action. Let's say we say, 50% probability of moving left, 50% of moving right. So it's not guaranteed that every time we're on some states, we're always going to choose one action. 50% of the time we might choose one, 50% we might choose another. So stochastic policies are all about randomness and exploration because, we're not doing the same thing in a state every time. In contrast, a deterministic policy always picks the same action given a state. This is a function mu of s that does not return a probability. It is returning the action that the agent should take. So there's no randomness here and there's no exploration here. Every time you're in state S, you're always going to return action A. Now you might be wondering, okay, seems okay abstractly, but what does this function actually look like? Well, to give you an example, let's find one type of function that will be a deterministic policy. It can be a greedy policy. So the greedy policy can be defined simply in words as just picking the action with the highest action value. And that's, tying together these action value functions and these policies. So now if the agent has some kind of action value that it has assigned to, let's say, different actions in different states. Anytime that it wants to pick an action, it can use that action value to guide its decision. Now, this is fine in words, it conveys the basic concepts, but I did want to introduce you to some math, we'll gradually sneak the math in. The way that we can write this out in mathematical form is this. So QS of A prime just means what is the action value in state S and action A prime. So what's, the expected future reward that we'd get when picking action A prime in state S. Argmax is saying take the A prime, take the variable A prime that will maximize this action value. So you can see how this is saying the same thing as pick the action with the highest action value, because the argmax returns the action that maximizes this, and that's the one that our policy will pick as the action that the agent should take. There's only one problem here, which is like we're using this QS of A prime term, whatever. We haven't defined what this function is. We need, a concrete equation, right? We need some way for the agent to estimate what is the action value for each action in some state. For now, I'm going to just define it informally, and next chapter we'll, add some more equations. But again, we have that same equation for the greedy policy, and I'll just define this in English. So we're going to estimate the action value for any state in action as the average reward that we've gotten in the past when performing that action in that state. This is called the simple averaging action value estimation. So this is one basic RL algorithm. In fact, it defines the key parts of an RL algorithm. So it defines the policy that the algorithm is using to choose the actions. It also defines the value estimates, how the action is deciding which actions are valuable to choose. And the two go hand in hand, they work together. So now to end off this section, where we talked about some basic jargon and started introducing in some very, very, very basic math, we will take a look at an example of just applying these two equations. So let's say we're playing a game of Dungeons and Dragons. It's kind of fun. You have like storytelling, different scenarios, and you roll dice to interact with the world, move the story forward, things like that. So let's say we're in D&D and we're in a casino environment. We need a RL agent to tell us when to place a bet. And here are the rules. So in the environment, we have to roll a 20-sided die, a d20, and let's say there's a dealer. They will tell us, here is the minimum score that you need to roll in order to win, which we will assign to the state. So for instance, the state could be 17 if the dealer tells us, hey, if you roll this die and get a 17, then you will win, some prize. The actions that the agent can choose are to either bet or not bet based on what the dealer says the minimum score is. And the reward that we assign to the agent so that it can learn to be successful is to bet when the roll succeeds or not bet when the roll fails. And obviously, using the minimum score that the dealer told us about, if it's a very high score, like let's say you need to have a 20 in order to win, then we'd like the agent to learn to not bet because, the roll would have failed, most likely. Or otherwise, try and get the agent to learn to bet when the roll is likely to succeed. So with this problem set up, we can apply the two formulas here in order to see how our RL agent behaves. First, we'll look at how the RL agent estimates the action rewards, and then we'll look at, what the policy selects in terms of actions. So let's say the dealer told us that the state is 13, i.e. we need a score of greater than 13 in order to win. In the starting 6 rolls, the agent, it bets and succeeds twice. So there were 6 repeated rolls. 2 of the times the agent decided to bet, and the bet did win. So with that information and this formula, what's the average reward for betting when the state is 13? Well, the average is, okay, you had 2 successes out of 6 rolls. The average is 0.33, so 1/3. Let's say the agent then rolls another 6 times, and it succeeds only once. So it bets another 6 times, and one of those bets succeeded. So now we can update our action values. So now we will say, okay, what's the average reward for taking the action of betting when the state is 13? Well, now we got 1 for each successful roll, so we had 1 plus 1 plus 1 out of the number of rolls so that we can have an average. So now it's 0.25 or 1/4. You can see the Q values are updating as the agent gains more experience. Now, this process would repeat for the other action of not betting, and overall, our greedy policy would select either to bet or not bet, depending on which one had a higher action value. Hopefully that gives you a concrete example of some of the math involved and, the key ingredients of any RL algorithm, which are the states, the actions, which, are selected with the combination of the policy function and the action value function, or the state value function. With that out of the way, here are a few quick questions to check if you understood the content of this section. I'd encourage you to pause the video and try them out. Okay, assuming that you've tried, let's go through them. So the first question, how is RL different from supervised learning? So supervised learning algorithms are like, preparing for a test, you get the answers. RL is all about trial and error. You do not have answers, you just have to trial and error your way into figuring out what the correct solution is. Next, how does a value estimate, like Q of SA, help an RL agent decide what to do? Well, we can define RL policies that use these value functions in order to pick which actions to take. So you saw earlier, mu of s is equal to the action that maximizes this function. So the RL agent decides what to do in in most cases, but only the one case that you've seen so far. It decides what to do by using the action values in its policy function. Finally, what does a deterministic policy mean? Deterministic just means that in every single case that we're in a given state, we will always pick the same action. So the opposite of that would be, say, stochastic policy, where we have probabilities of picking different actions in one state. With that being said, you survived the first checkpoint on RL Jargon, and take a pause if you need to, but when you're ready to continue, we will continue with the RL math section. So this next section, it might be tricky for people that haven't taken a probability course. Luckily, it's only like 4 slides, so if you are stuck, it's easy to get unstuck with ChatGPT. Let's get started. To begin, I'm going to quickly do a reminder on what an expected value is. Here's the formula for an expected value. I'm going to explain it with an example. Let's say we have, we're buying a lottery ticket. It has a 1% chance to have us win $100. a 10% chance to have us win $10, and the rest of the time we're not winning any money. If we ask the question, how much do we expect to win? So that's what the capital X is, our expected winnings. I think you'd agree with me, it doesn't make sense to simply take the average of 100, 10, and 0, because each of these outcomes are not equally likely. That's what the expected value captures. It's not just saying that our expected winnings are the simple average of all the different outcomes. So little x represents $100, $10, and $0, the different amounts that our winnings can be. It's not just saying that it's the simple average of that, it's saying it's the weighted average of that, where the weights are, how likely is each of these situations to occur. So here we simply say if there is a 1% chance for us to get $100, well, we weigh the amount of money that we could win with the likelihood of that occurring. So we do 0.01 times 100. Similarly, for 10% $10, we have that here, and 89% $0, we have that here. This sigma symbol over here, so sigma x, it just means we're summing over all of the possible lowercase x values, which are all of the possible outcomes in terms of what we can win. And if we punch that into a calculator, we get 2. So that's what we can expect to win. On average, on weighted average, I should say, we would get $2. A related concept here is a conditional expected value. It's actually not very conceptually different. All the difference is that we assume certain conditions have happened and then compute our expected value. It is still a weighted average. The intuition is still the same. The only difference is when it comes to computing the probability, we assume certain conditions before we determine, what's the probability of each outcome happening. As an example here, if we wanted to predict, how many millimeters of rain can we expect today? So the millimeters of rain would be capital X. Lowercase x could be like, 0 millimeters, 1 millimeter, 2 millimeters, and so on and so on. Yes, technically, I need an integral here, but I can't be bothered. So just a sum, it's fine conceptually. If we wanted to predict, what is the expected amount of rain that we have today, you have capital X, but we wanted to bake in certain assumptions into our prediction. So let's say we assume that it rained yesterday, so y equals 1 for it raining, and it wasn't sunny yesterday, z equals 0 for it not being sunny. Then we can use this formula. And the only difference is that we change the probabilities because, if it rained yesterday and it wasn't sunny yesterday, then it makes it more likely that it's going to rain today. So that's going to change the probabilities of how much rain we get today. One last thing that I wanted to introduce is how we can go from an expected value where we have assumed certain conditions to an expected value where we have assumed fewer or just no conditions whatsoever. This process is called marginalization. This is the key formula. Again, I'll explain it intuitively. Let's say again that x is the amount of rain in millimeters that we expect today. Y equals either 0 or 1. Those are the two possible values that y can take on. Depending on 0, it didn't rain yesterday. 1, it did rain yesterday. So what is this formula doing? Well, we'd like to figure out what is the expected value in terms of how much rain we have today. But what we know is the expected value already computed based on certain assumptions. So let's say we've computed how much rain we expect today if y equals 0 or y equals 1. How much rain we expect today if it did rain yesterday, if it didn't rain yesterday. This formula is simply saying how we can use that information in order to figure out in general putting aside the assumptions, how much do we expect it to rain today? So we just take our estimates for the two cases, for the two possible assumptions, and then we multiply them by the probability or the likelihood of each assumption being true. Add together those results, and that will give us, the general expected value free from any assumptions. Hopefully that intuitive walkthrough makes sense. The last thing I'll note is that often we will add subscripts right here, right after the E sign to indicate which variable we're summing over. So for example, here I could do E sub y because I'm summing over the y variable. Here I could do E sub x because I'm summing over the x variable. In RL, we'll often either sum over the actions, E sub a, or the states, E sub s. Hopefully that's not too boring for people that already know expectation, and if you don't, well, hopefully that gives you some questions that you can ask ChatGPT. Moving on, let's talk about some more RL-specific equations. The first thing I want to define is I mentioned this idea of total future reward. I said the goal of an RL agent is to maximize the total future reward it gets. But, what is that? How do we define total future reward? One definition is to say, okay, let's say we're getting, rewards over time. So we get R0, that's our first reward, then we get R1, then we get R2, and so on and so on. What can we do with that? Well, let's just say we add them all up. That's our total future reward. It's just the sum of all of the rewards that we've gotten. The problem with this is that, well, as you can see, if we keep adding things over time, this is going to blow up to infinity, which is going to be very inconvenient because we're going to be doing math on this total future reward. That's what G of t is. The other annoying thing is that it assigns equal importance to each of these rewards that we're getting. But often in reinforcement learning, we want our agents, we want our algorithms to prioritize future rewards less than current rewards. We want them to understand, hey, the environment may change in the future, or assumptions may change in the future. So don't count too much on maximizing, some reward that you might get 100 steps later. Optimize for the reward that you're getting right now. In order to do this, what we do is we introduce a discounting factor. The discounting factor is literally just a number between 0 and 1 that we multiply each reward term by an extra time, such that each subsequent reward term into the future, it becomes lower and lower. So for instance, let's say we had gamma equals 1/2, so this is gamma. If we had gamma equals 1/2, then we're multiplying here by 1/2, here by 1/4, here by 1/8. You can see we are cutting down the size of each future reward such that future rewards are worth less than immediate rewards, the first reward that we got. We can rewrite this in fancy math notation if we want. Here's the fancy math notation. You'll see this, but it's just the same idea here. So as long as you understand this conceptually, it's okay. Now, there is one alternative form to write this that is actually important to note. So if you think about this logically, let's say we're trying to find the future reward at time t. Well, it's going to equal to whatever the current reward is plus the, future reward after that, right? So future reward across all of time is whatever we just got at time t plus future reward at, whatever time is remaining. Makes sense, it's logical. So we can write this equation like that in a recursive form. Just keep in mind that this future reward, because it is an extra time step in the future, it needs to be discounted by having a gamma, multiplication. So this is our recursive form for this equation, which we will be, using pretty often. Now that we've defined expected value and future reward, we can actually update our definitions of the action value and state value to make, general sense in theory. So the formal action value definition is pretty simple. We just say that the value of taking some action in some state is the, expected value, the weighted average of the return that we can get. Why does that make sense? Well, assuming that we took a specific action in a specific state, this term will tell us how much return can we expect going forward. Not just, average of the possible values of the return, but the weighted average multiplied by the probability of each return value we can get. That's why it's a general, useful definition for the action value. Now, keep in mind that there are, specific implementations that won't use this general theoretical definition. They might use simplifying assumptions, like, let's say, assuming all the probabilities are the same, or, assuming that we're using some particular gamma value when computing the return. So we will have specific algorithms that will approximate this general definition in different ways. The last thing that I wanted to mention in this formal math section is defining the state value. One way to do it is simply be like, hey, pattern match. If, the action value function has this format, well, the state value is not associated with taking a particular action, so we just remove that condition in terms of the list of assumptions, right? We just say, hey, we're not assuming A of t equals some particular action. It can be any action. The more interesting thing to note, though, here is that, well, these two equations have a very similar format, minus a couple of equations, minus a single assumption, a single condition. Can we rewrite this equation to look like the second equation? Well, we can do so if we use the definition of marginalization that I just gave 2 slides ago. So again, marginalization goes from having more conditions to having fewer conditions. If we pattern match, the condition we want to get rid of is AT equals A, so that's like Y equals Y over here. So what we're going to want to do is take the full expectation, which is QS of A. So take this full thing, plop it in here, then multiply by, the probability of the action being each possible action, and sum over all the possible actions, which gives us this. So if we want to go from this expected value to this expected value, V of S is going to be this formula. QS of A is the full expected value, like over here. Pi of A given S, remember that's the probability of choosing each action given a certain state, aka the probability, the policy probability distribution. So that's this probability over here. And finally, we sum over all the possible actions. The nice thing about this equation is that it relates the policy, the action value function, and the state value function, all in one equation. The last thing I'll note here is that we have, some number over here multiplied by a probability, and we're summing over all the possible, actions that we can include in this probability. Well, that's just the definition of an expectation, right? An expected value is just a weighted average of the possible values multiplied by their probabilities. So we can rewrite V of S, given that this is a probability distribution, we can rewrite it in this format, where the A tilde pi of A, lots of reading, but this just means that we are choosing an action from our policy. And that makes sense. We're saying that the value of our state is the expected value of our actions, given that we select our actions with this particular policy. So overall, if you want to check your understanding of this section, quickly pause the video and try and answer these questions. Assuming you've had a go. So I want to do this question first. How does the state value function relate to the action value function? Well, the action value function is just whatever our expected return is, right? Whatever the return values are, assuming that we picked a specific action in a specific state. The state value function just gets rid of the picked an action part of that equation. It does not assume or condition on us picking a certain action. Instead, it computes all of the action values and then multiplies them by the probability of having picked each action. It takes the weighted average across all that. Over here, we ask what happens if we set the discount factor gamma less than 1? Well, we weigh future rewards lower than immediate rewards. If we set gamma equals 0, then all future rewards are going to be, eliminated entirely. Only the current reward matters. And this should be gamma equals 1. So if we set gamma equals 1, then all rewards are weighted equally. So we just have the R0 plus R1 plus R2 plus R3 case that we saw earlier without any discounting. With that, we have finished our second section on RL Math. Now we will look more into some policies we can define. Take a break and come back when you're ready. Okay, we have a pretty straightforward section here. Before, we just defined one type of deterministic policy. Now let's expand that, consider some alternatives, including both deterministic and stochastic policies. So the general idea that we want to talk about here is how we optimize for exploration versus exploitation. Here's what I mean. When it comes to exploitation, it refers to an RL agent using what they know already in terms of, current action values, state values, whatnot, which actions are good, to pick what they're going to do. This is analogous to when you go to a restaurant and just order your favorite dish. You do not try new dishes to find something you might like better. You just go with what you know. In, contrast, we have exploration, trying new things, random things. Going to the restaurant and ordering some new dish. Even though you might not like it, maybe it leads to some dish that you hadn't tried before and that you might enjoy even more. The thing is that we as humans, but also as RL agents, must balance both of these. We have to know when to explore and when to exploit. And one way to control that is with the policy we use, which is why we have this section on different policies that we can implement. As a reminder, we talked about the greedy policy, which is just, a deterministic policy. We choose the action that has the highest action value. There is no exploration. It is 100% exploitation. Now, just to get you used to the, notation that we'll be using for stochastic policies, where we have some probability distribution that tells us the probability of choosing different actions given the state we're in, I'll rewrite this policy all in an alternative format. So now we have a probability function. It assigns the probability of us choosing some action A to be 1 or 100%. It does this when A is the action that has the highest action value. In all other cases, we have a 0% probability assigned to all other actions. So these are two ways to express a greedy policy, one that only exploits all of the time by picking the action we know to be best. Now let's look at an alternative. We want to incorporate some exploration in here, we want a stochastic policy that does not choose the action that we currently estimate to be best all of the time so that it can discover more actions. One simple type of stochastic policy is an epsilon greedy policy. So most of the time it's greedy, it's just doing the action is just the argmax, that you just saw over here. But some percentage of the time it's choosing a random action just to explore. I've written this out in Python format code. So you generate a random number between 0 and 1, and if it's less than some epsilon, some parameter that you choose, you will choose a random action instead. This is just saying some percent of the time, that depends on the epsilon you set, you choose a random action so that you can explore. This is pretty simple, but it's fine. It's a stochastic policy. It's our first policy that does not return the same action every time you go to a specific state, because sometimes you will just return a random action. Note that I've written this out in pseudocode here because the math is just, it's the notation is a little bit clunky, but here in pseudocode, the idea is very simple. Now, this stochastic policy, as I said, it's pretty simple. One of the problems that it has is that as the action values change, as Q of SA changes, it can suddenly be like, you had most actions at 0.01, and then one action increased like maybe like a minuscule amount in terms of its action value, but suddenly it now becomes the argmax. So just tiny, tiny changes in the action values can result in drastic and sudden changes in the actions we select. Among other drawbacks, this motivates us to try and find a better stochastic policy, one that can do exploration and exploitation, but not have, that kind of drastic and sudden change behavior. That's how we get the softmax policy. Now I'm going to motivate this in steps. Let's just say that we assigned the probability function, so our policy function. Let's just say we said the probability of choosing the action A is it's equal to the value of that action. This doesn't make much sense because the action value, that could be like 10, but you can't have a probability of 10. Probability has to be in range 0 and 1. So the first change we're going to make here is we will divide the value of the current action by the sum of all action values. This is what we call normalization. So now the probability of each action will be 1 proportional to its action value, but furthermore it will always be between 0 and 1, because each of these things, each of these terms will be 1 over the sum of all the action values. Now, the only problem with this formula, it does the normalization and it does work. It gets the key idea across. We're selecting actions with higher probability proportional to their value. The only problem is that often the action values are very similar. They're very close and there are tiny differences in them. Let's say like, most action values are 1,000 and then one is 1,001. This doesn't result in a meaningfully different probability of picking that higher action, the higher action value. So in order to fix this, we introduce basically a bigifier function is what I'm going to call it. It's just the exponentiation function. So we do e to the power of whatever the value is. This will just make tiny differences bigger, because there's a bigger difference between e raised to the 1001 and e raised to the 1000 compared to just 1001 minus 1000. So this function and this function are the same idea, normalize, have the values, but tiny differences are accentuated more. Lastly, we add in a temperature parameter to control how much differences are accentuated. So we take whatever our values are and then divide by some temperature parameter tau. So for instance, if we divide by 10, you know, a difference of 1001 versus 1000, now that is not, what it used to be. It used to be that the difference is 1. Now it's going to be 1 divided by 10 because the temperature was set to 10. Effectively, what this results in is it allows us to control the level of exploration versus exploitation. If we set a high temperature, it's going to make all of the action values have smaller differences in between them. So the algorithm is likely to be more stochastic. If we lower the temperature, it's going to be like, the different Q values have more differences. The algorithm is going to be more deterministic. And we can control this over time, right? We can start off with more exploration with a high temperature, and then reduce the exploration with a lower temperature. The other thing to note is that unlike Epsilon greedy, we do not have any argmax. All the actions have some probability of being chosen, which results in smoother changes. The probability of being chosen just goes higher for some actions. It's not like before the argmax always returns one value and now it returns some other value. There is a smooth change going on. To show you this visually now, let me show you some graphs that compare the cumulative reward that we're getting over time over, let's say, the number of time steps. I'll define this term later. So I have a few different graphs. Let's focus on the epsilon greedy, those policies being used. In this case, the RL agent, you can see it has like very spiky behavior. The reward that it's getting over time, it fluctuates a lot. Why is this happening? Because in the epsilon greedy case, we're always forced to pick we're always forced to pick some random actions, epsilon% of the time. So if epsilon equals 0.3, that's like 30% of the time we're choosing randomly. So you'd expect a lot of fluctuations. With the epsilon equals 0.1, this orange line, you can see we still have fluctuations. They're just smaller because we're only choosing random values 10% of the time. In the softmax cases, you can see we still have some fluctuations, but the fluctuations are smaller, especially as we have a smoother policy. We're just changing the probability of different actions. We're not being forced to always pick a random action just for the sake of it. The other thing I'll note is that the epsilon greedy algorithms, they reach an asymptote, they converge to a lower reward than the softmax policies. Why is this? Again, it's the key idea of an epsilon greedy algorithm is always picking random actions. That's going to hurt the maximum performance it can reach because it will, no matter what, it might have learned, the best Q values, so the best action values. It will still occasionally just pick a random action, and that will reduce the average reward that it can get over time. In contrast, the softmax functions, they can get closer towards the maximum theoretical reward because they're not ever bound to, choose random actions all the time. They are learning what the probabilities of each action are, and if one action is clearly the best, then they can approach a near deterministic policy where it's like one action has 99% of the probability and all of the other actions are almost never getting chosen. So that makes softmax more flexible than epsilon greedy. It can start off being stochastic and then it can end up approximating a deterministic function. Last thing I'll note is that the speed of us converging is influenced by the temperature we have. Also, the the final value that we converge to, the final reward, is also influenced by the temperature we have. As we have a higher temperature, all the actions are, closer together in probability. So we're choosing lots of different things, we're exploring lots. That's why we're not growing as fast. But because we've done more exploration, we end up with a more optimal, knowledge of all the different actions that we could select. In contrast, the lower temperature one, because it's, choosing the better actions more often, the better actions are more, they're assigned more probability compared to the worse actions. It can more quickly start to grow, but it doesn't converge to a final reward that's as good because it has done less exploration. Hopefully that makes some sense. If you want to check your understanding, pause the screen and I'll, talk about these answers in a sec. Okay, assuming you paused. First thing, why can't an RL algorithm always choose the best actions it's learned? It's because we need to explore different actions to figure out if the actions that we've learned are in fact the best actions possible or just the best actions that we've discovered so far. We also ask what are the pros and cons of a higher epsilon in an epsilon greedy policy. Well, from the graph that we just showed, having a higher epsilon means that we will be doing exploration more of the time. So that tells us, okay, we'll more thoroughly explore the possible solutions. It might uh, it might allow us to discover better actions, but the problem is that we converge to a suboptimal value because in the end we're still selecting random actions, say 30% of the time instead of 10% of the time. So we trade off some speed of discovering better actions more quickly with having a optimal final reward. Finally, what are the pros and cons of softmax versus epsilon greedy policies? Softmax has smoother changes, whereas epsilon greedy, it might suddenly switch from choosing one action all the time to the other action because the action values have changed and that made the argmax return a new value. Also, epsilon greedy policies, as we saw, they converge to suboptimal rewards compared to softmax functions. Often they're slower as well because softmax can do more exploration given that it's always, assigning certain probabilities to each action, which we can control via the temperature to control the exact level of exploration versus exploitation, which allows us to have more stochasticity at the beginning and have a more deterministic policy at the end. With all that, we have finished defining some alternative policies. Now let's return back to the idea of defining how to estimate the action value functions. We will get started with the next chapter whenever you're ready. We're now going to explore the simplest type of RL algorithm, which fits into the category of action value methods. The reason why this category of algorithms is simple is because it only applies to problems where there is a single state and multiple actions. So for example, let's say we have to bet heads or tails on a coin flip when we don't know what the probability is that the coin will give us a heads. It's an unfair coin of some sort, we just don't know how. So the two actions we'd have are heads and tails, and the state is just whatever the probability is of the coin giving us heads. In this context, we often write QS of A as just QA because S is always the same fixed state. Now, Algorithms that solve this type of problem are called action value methods. They have a few key features. First, they don't need much memory because each of these action values can be simply stored in a table. That's very obvious in this case where we have literally just two actions and just one state. So we store two action values, Q of heads and Q of tails, to tell us, do we bet heads or do we bet tails? This is one of the first tabular methods that we'll learn about. Tabular meaning we're storing the action or state values in a table. This is very simple because, you can't always do this. Some other types of problems, you might be using much more memory and that wouldn't be possible. Now with that out of the way, let's talk about how we can define our value functions in this simplified case. I already showed this value function to you. It's the simple averaging value function. So we mentioned this in a previous context where we said, okay, give us the average reward for taking some action in a given state. Now there's only one state, so we simplified that further. So if we define our value functions this way, we can simply say that the value of each action is the total reward we've experienced divided by the number of times we've taken that action. Now, to define this with less English and more math, I can introduce this expression where NA is the number of times that action A is taken. Ri is the reward from the ith time that we take this action. So over here, what we're doing is we're summing the rewards from all of the NA times that action A has been taken, and then we divide by NA to get the average reward instead of the sum of all those rewards. Now, this is enough for us to actually implement, Python code for some kind of RL algorithm. Let me walk you through all of this pseudocode. So here we have a Q value table. So it will map state action pairs to values, but in this case, we always have the same state. If we wanted, we could, skip that and just map actions to values. Next, we have a count, which maps actions taken in the one state to the number of times that action was taken. Returns, similar idea. We, map the actions to the total reward accumulated across all of those actions. And then here we have a list of possible actions. So we're implementing a greedy policy from section 3. So we're just taking the argmax. So whatever the highest action value is, we will take that action. When we are updating our action values, well, we do it with the formula we just defined. So the total rewards divided by the count. Well, we just need to update the count and the rewards that we just got in the current time step if we want to update the Q value that way. Note that I'm implicitly using in this formulation, so this formula, I'm implicitly using a gamma value, a discount factor of 1. That's why you don't see those terms anywhere. Finally, now that we've defined the policy and the value function, we can define the RL loop. So we have some environment here that is passed in. The environment, it is some function that's passed in with useful methods like reset, which brings us to the initial state that we're in. In this case, it's just the one state that we can be in. We select some action, we implement that action, and the environment goes to the next state. In this case, there's only one state, so we're still in the same state. We get a reward, and we get the done flag if the simulation has ended. So we can implement different conditions to check for when we want to finish. After we get the data of, here's the state we're in, the action we selected, and the reward we just got, we update the action values, and then we move forward to the next state. If there were multiple states, this would have an effect. In this case, it doesn't. So we keep repeating this, where we pick an action, and then we update the queue table, which changes the action we pick for next time, and so on and so forth. So this is a proper RL algorithm. We can use it to solve real problems. Now, one thing that you might have noticed in the prior RL algorithm is that it's a little bit inefficient to, for instance, just keep storing all these returns all the time, keep the count going. We have to maintain this data, which takes up a lot of memory. To fix this issue, we can rewrite this update in a way that is more efficient to compute. Now, this is the final results we will get. In the next slide, I will prove to you why this is equivalent, why these two statements are equivalent. The final result form is a common form that we'll see a lot. It has the format of a new estimated Q value at time step n. It's based on the old estimate here, plus some target value minus the old estimate being multiplied by some step size, 1 over n. This form comes up a lot because it's it's one example of a mathematical technique called fixed point iteration. Eventually, if we keep doing this, then over time, the Q values will not be changing anymore. And in general, whenever you see equations of this form, so this general format, the new estimate is going to be slightly closer to the target than the old estimate used to be. That's how you can interpret equations of this form. So now let me prove to you that these two equations are equivalent. This is the first of, I think, 3 proofs that we're going to have across these slides. So first off, we start with the original definition. Remember, NA is the number of times we've taken action A. Ri is the reward we got when we took action A for the ith time. Here, I've taken out the last term, so RNA, the last reward I got. And here are the other, previous NA minus 1 rewards that we got when taking action A. Multiplied by 1 doesn't change anything. NA minus 1 divided by NA minus 1 is indeed equal to 1. You'll see why I, broke this down this way in a sec. Over here, I took the numerator and brought it outside these parentheses, and I took the denominator and brought it inside these parentheses. Now, if you notice, check out this expression versus this expression. The only difference is we are summing to NA minus 1 time steps. We're not summing to all NA times, but otherwise the expressions are the same. So this is in fact Qn minus 1 of this action, i.e. this is the old Q value that we had before we ran the update. Now I'm going to distribute these terms over here. So NA times this minus 1 times this. And finally, what we have is, if you take this term over here, we have NA over NA times Qn minus 1. These two will cancel out, and we just have Qn minus 1. After that, we have 1 over n, so n is the number of terms that we're using. So n equals NA. Anyways, we have that times R of n minus Q of n minus 1. That's where this part comes from. This term plus this term. And that is the proof done. So why would we use this form? Well, it's more efficient. We can just store the old Q-value estimate and the new Q-value estimate without having to store all of the rewards that we've gotten over time. So we don't have to store this returns field, which is like what is the sum of the returns we've gotten over time. We can just store the Q values. Now, I'm going to introduce a different method of updating our Q value estimates, one that addresses a limitation of the simple averaging that we saw, which is that this simple average changes very slowly. So here's how the exponential average works. We have basically the same format that we just saw, except instead of using a step size of 1 over n, which is just going to get smaller and smaller and smaller as you get more and more experience with that action, we use a fixed step size of alpha. This allows us to keep the step size high enough so that we don't have increasingly tiny changes, resulting in a Q value that is not being updated over time. So it makes recent rewards matter more than the simple averaging case. Again, the only thing that's changed is the step size. It used to be 1 over n, now it's alpha, which is some fixed constant. That's the only change. Everything else is unchanged. To show you visually the impact of this change, just changing the step size, here's a graph. So let me walk you through it because it can look a little bit complex right now. What we have going on here is the red line shows how a Q-value estimate is changing with the simple averaging technique, where the step size was 1 over n being the number of times we have taken that action. And then the blue values are the exponential averaging method with an alpha equal to 0.1. Now, the problem that's happening here is, again, that problem of estimating whether to bet on heads or tails if we have a coin with unknown probability that, we don't know what the probability of having heads is. Now, at the dotted line, I'm saying the probability of the coin changes. Let's say someone like swaps the coin on us and we don't realize. And then you can see what happens after this change occurs. Let's say the probability of getting a heads goes up and we win money every time there is a heads. That would indicate that the Q value should go from, whatever their old regime was to some new level of, rough convergence. You can see that the simple averaging technique, it's stable because like there's not much change going on after we've had 400, 500, 600 time steps. So it's stable, but it's slow to react to this change in the environment where now we have a new, we have a new probability for heads. In contrast, the exponential averaging in blue, you can see it's always very spiky because it's, paying attention to recent changes, and the step size is always, it's alpha, so it's a fixed constant. It doesn't go down over time. This makes the Q values more volatile, but when the environment changes, the Q values much more rapidly also converge to the new value that they should be at, while simple averaging hasn't caught up. This shows one of the benefits of exponential averaging versus simple averaging. Simple averaging is more stable. However, exponential averaging, it is good for non-stationary problems. Non-stationary is this keyword that comes up a lot of times in RL. It just means that something can change in the environment that requires you to come up and adapt to a new solution. So this shows you one of the trade-offs of different RL algorithms, with the difference being, which type of action value estimation you use. It can affect how well the RL algorithm can adapt to new environments versus be stable and reliable in a single environment. So to wrap up, here are two questions to check your understanding in this section. Give it a pause and then we'll take it up. All right. So question one, what kind of problems is the action value set of methods for? There's more than one. As you saw, we can change about different algorithms by adjusting, the types of policies being used, the types of action value estimates we're doing. So this set of algorithms is good for problems that have a single state and multiple actions. Ideally, they're non-stationary problems, but they can, sorry, ideally they're stationary problems, so they don't have big changes in environments because this is a simplistic technique. Though we do have some tools in our toolkit, like exponential averaging, in order to deal with non-stationary problems as well. Now, that is the hint about the second question. It's non-stationary problems where exponential averaging is better than simple averaging, because exponential averaging can react to the changes in the problem. It can react to and adapt to the new environments. With that said, that's the end of our first set of RL algorithms, which is action value methods. Take a break, and I'll see you in the next section. Next up, let's talk about temporal difference, or TD learning. It is the basis of many modern RL algorithms. To explain the key concepts, we need to define a little bit of jargon here. So the first thing to note is a trajectory. It's basically like a log of the events that an RL algorithm has experienced. So all of the states, actions, and rewards that the RL algorithm has seen. Let's say it starts off in state S naught, takes action A naught, and gets a reward R naught. Then it transitions into the next state, takes the next action, gets the next reward, and so on and so on. If the trajectory is finite, i.e. it ends at some point, we call the trajectory an episode. So the trajectory must have a terminal state, which is a state where you get to the end of whatever the task is and you have to reset. As examples, let's say you have a maze solving task. If you get to the end of the maze, then you have solved the maze. That is the terminal state. Nothing else happens after that. You just reset and, solve a different maze. Same idea while playing a game of chess. If you end up with one player not having a king, that is a terminal state. The game ends and you now have nothing else to do. You go on to the next game. Last thing to note is something called the Markov property. This is needed for proofs in TD. So it's one of the assumptions about trajectories. We assume that the current state, ST, it has all of the information we need to continue forward. So if we know S1, then we can figure out A1, R1, S2, A2, and so on. Everything that happens after. We don't need S0, A0, and R0 if we already know S1. With that out of the way, let's define the key aspects of TD learning. The main problem that it tries to solve is that when we have methods like simple averaging that we saw earlier, they can tend to be slow to get good estimates. Why is that? Well, we have to wait multiple time steps, maybe up to the end of the episode, to actually update the values. Why? Because if you recall what the formula was, we sum up all the rewards we got when taking action A, then divide it by the number of times we took some action A, i.e. we're figuring out what is the average reward we get when taking that particular action. And this requires a bunch of data points. If we only, let's say use one particular reward we got, that could easily be an outlier. So simple averaging and techniques like that, they are slow to form good value estimates. Another technique that is worth searching up that I skipped over in this particular presentation is Monte Carlo methods. So they are methods that also have this problem where you have to wait until the end of an episode before you can make estimates of your returns and subsequently your action and state values. Now TD, it solves this by using bootstrapping. Bootstrapping is where you use current estimated action or state values to update other action or state values. You do this at each and every time step so that you can move more quickly. This may sound abstract. Let's dive into the details and you'll see why I say this. So the underpinning of TD is something called the Bellman equation. This can be a little bit, challenging to prove if you don't have university level probability background. So I will warn you when I go into the formal proof. For now, I'll give you a hand-wavy version. I claim that this Bellman equation is the recursive version of this equation that we already showed earlier, which is that the state value is just whatever the expected future reward is if we assume that we're starting from that particular state. So why would this be true? There are, I can wave my hands in different ways. If you reason about it, it seems kind of valid, like, v s of t plus 1, it should encapsulate all of the information about, the rewards from time step t plus 1 onwards. If we add to that r plus, so if we add to that the current reward, rt, plus, discount that future reward, well, you can kind of see why this kind of term would be related to the state value over here. Another thing I can do to wave my hands and just do intuition is I can work backwards and show you that, this recursive formula is computing results in the format we want. So the terminal state, S at capital T, that's the terminal state there. We can see that the value is 0 because, well, nothing's going to happen after. We can't get any more returns. The episode's over. At the state before that, we can use this Bellman equation. And what do we see? Well, we have the reward at time step t minus 1 plus gamma times the reward at the next time step. But this is 0, as we just said. So we just have, this expression. R of t minus 1 is a constant, so the expected value of a constant is just that same constant. Constant can't change. If we continue this forward, the state before that, s of t minus 2, we just again use this Bellman equation. We have r of t minus 2, and we have the, state value we just computed. We plug it in. All of this stuff is a constant, so we end up with a constant. We can keep repeating, so s of t minus 3, that reward, gamma times whatever we have up here. And when you simplify everything, then we have r of t minus 3 plus gamma r of t minus 2 plus gamma squared r of t minus 1. If you, recall, that is very much the format that we were expecting, right? We were expecting g of t to be, a sum of rewards that are being discounted as you move more and more heavily into the future. So this is the hand-wavy explanation for the Bellman equation, which is the recursive version of the definition we had earlier. Before I move into the proof, I'll just do one last thing, which is to restate this in action value form. So If we want to extend this to action values, well, we just use this definition that we had from earlier. We showed this in a prior section. So we just plug this into the Bellman equation. We get this, where I just, because this is s of t plus 1, I just put t plus 1 everywhere. So a of t plus 1, s of t plus 1, and so on and so forth. Let's say we are using a deterministic policy, or we have a stochastic policy like the Softmax, which has over time converged so that it is now basically always going to be the well, basically a nearly deterministic policy, like 99.99% of the time, you're just choosing one action and then you very rarely choose other actions. In that case, this probability, sum, this thing, is going to not have a bunch of terms. It's going to just have this probability being 0 most of the time, and then 1 for one particular action, which is the action that maximizes this Q value, this action value. So we rewrite the equation like this. So this is the Bellman equation in action value form. Now that we've hand-waved our hands enough, I'm going to do a formal proof of this Bellman equation, and then you can use this to go from the proof that I do to proving the action value variance. The warning I will give to you right now is if you haven't taken a university level probability course, this is going to look messy, and I do not at all, look down on you if you decide to skip this. Let's get started. So this is our definition of the return from earlier. We have a reward plus gamma times, the return plus gamma times the future return. And we also have this definition from earlier. So the state value is just the expected value of the return, given that we're starting from some state. Let's substitute 1 into 2, and we get this equation right here. Next up, I'm going to do something that is going to feel confusing. I'm going to introduce another condition into my equation. The way I'm doing this is just using the marginalization rule that I introduced in reverse. So the marginalization rule I said was how you could get rid of a condition so that you could go from here to here. Now I'm doing it in reverse. So if I want to add a condition on the action in here, then I have to introduce all of the probabilities across all of the actions and then sum across all of these, weighted expectations. That will give me the original over here. So reverse marginalization. I'm going to do this a couple of times in this proof. Now, one thing you might notice is that this probability of taking given action given some state, that is the same as our policy function, right? That's what our policy function does. It's just a short form for the probability of taking some action in some state. So I just replace this notation with this notation. Now I'm going to copy this equation to the next slide. Here we are. I haven't changed anything. Just copy it over to the next slide. Next up, what I'm going to do is condition some more. So now I'm conditioning on R of t and then S of t plus 1. Again, I perform the same step where I'm summing over all of the probabilities that I've introduced. Next, I'm going to use the Markov property, where I will realize that with the Markov property, I only need to know S of t plus 1 in order to figure out everything that I need about the trajectory. All of this information, S of t, A of t, R of t, is irrelevant. So what I can do is I can just remove all of these conditions. If I do that, well, I'm able to do two things. One, you can see I'm left with only the S of t plus 1 condition. But two, if I got rid of this R of t is equal to this particular value, now R is just any old constant, right? It's being summed over here. So whatever value of R we have, that means I can treat it as a constant and factor it out of the expectation, because the expectation doesn't depend on our, having a particular value that is relevant. So I've moved the expectation inwards to just g of t, and the rest is just encapsulated by these square brackets. Now what I can do is, if you take a look at this carefully, so the expected value of g of t plus 1, given that we're in some state, well, it looks pretty similar to the definition of a state value. Just replace t with t plus 1. So realizing that, I can replace this expected value with v of s prime, the next state. Finally, all of these terms over here, they're just probabilities. So I just, throw those into an expectation. This is the value, these are the weights, and we just use this notation for the Bellman equation. That's the expected value of this when we are choosing actions given our policy, and we're summing over all, possible next states and rewards. So that's the Bellman equation. It's a little bit messy, but it's okay. You can use the hand wavy version. Now, given that we've established the Bellman equation, we're ready to move on to the actual TD learning formula. So here it is. I'm going to actually introduce all of the equations on this slide so that I can compare. So this formula, it follows the good old format for fixed point iteration. Let's say we have some new estimate, so we want to get an updated estimate for v of state s of t. We're going to use our old estimate, so v of s of t as it was before, plus the step size, which is alpha, and then multiply that by the target. The target here is the TD target from the Bellman equation. It's this thing right here. That's the target. So it is the current reward plus gamma times the state value of the next state. That's the target minus the old estimate that we had. So that's just fixed point iteration. One thing that I wanted to highlight for you is, vocab, this entire thing, target minus old estimate, that's called the error, because we're using the TD target. This is called the TD error. We can also compare this to the action value exponential averaging, because we saw that earlier, and or simple averaging, which we also saw earlier. The only difference from the action value exponential averaging is that the target has changed. Here it is simply Rn, the current reward we got. Over here we have the current reward plus gamma times the state value of the next state. If we were to compare to the simple averaging, we would have that change plus this alpha would be 1 over n. Anyways, you can see that the format is similar, but the main difference is that we are bootstrapping. We're using an estimate for v of st plus 1, so that's an estimate. We're using it to update our estimate of v of s of t. So we're using an estimate of state b to update our estimate of state a. That is the crux of TD learning. Now we're going to stop to check understanding because that was a lot. And then after a quick pause, we'll get back and introduce pseudocode for this TD learning section. So quickly pause and try these questions out. Assuming you've done that, let's carry on. So first thing, why is TD learning faster than simple or exponential averaging? The main idea, it does depend on the way that we implement, but the main idea is that usually these will require multiple time steps to get a good estimate. In some cases, you can search up Monte Carlo algorithms in the textbook. You will need to go over an entire episode before you make any updates. TD is faster than that by using bootstrapping. It uses estimates of our state value function to update estimates of our state value function. That is what is meant by bootstrapping, using estimates to update estimates. And finally, when we compare the value update for TD versus the exponential action value method, the main difference is the target, as we see here. So this is a bootstrap target, and this is, just taking the current reward. With that, take a break. That was a lot, and then come back. We'll introduce some actual pseudocode for TD learning algorithms. To wrap up the section on TD algorithms, I'm going to show you two practical examples of TD algorithms with some pseudocode that you can implement. The main categories of TD algorithms are going to be on versus off policy algorithms. When it comes to on policy algorithms, this is basically everything that you've seen so far. This is a general category of algorithms, and the specific on policy algorithm in the TD context is the SARSA algorithm. The main idea with on policy is that we just have one policy that has to balance exploration and exploitation. In order to do that, usually we have a stochastic policy, for instance, Epsilon greedy or Softmax, and that policy must handle the exploration part to learn about new actions it can take, but it's also used to figure out the best action values in order to do the exploitation. Now, this is simpler, but balancing the exploration and the exploitation, that can be tricky. So an alternative to that is off-policy algorithms. For instance, the Q-learning algorithm in the TD context is off-policy. Off-policy just means that there is a separate policy for the exploration versus the exploitation. So exploration is done with some kind of stochastic policy that has some randomness built in, whereas a greedy policy is used for exploitation. The explorative policy, it's called a behavioral policy. It's used during the training. And the policy that is more deterministic, that chooses the best optimal actions used so far, that is called the target policy. It's what will be used after the training is done. To give you an analogy as to why this distinction matters, consider the game of Monopoly. Now you're buying different properties, you could buy a blue set of properties, a green set of properties, and so on. Now, if you knew how to play Monopoly well, usually you'd fall into some kind of pattern. This is the strategy that you usually go for. But let's say you're learning for the first time. In that case, you might use some random coin tosses to decide whether to buy each property. Why? Because it lets you explore different sets of properties that you might buy, so you can learn how to use different mechanics within the game. Now, the on-policy versus off-policy concept, it will determine the strategy you end up learning that you take away from that, training phase when you're actually playing with other players. If you have the on-policy concept, what that means is that this randomness in terms of, sometimes using coin tosses, that gets baked in to the strategy you use after you're done your training. You're going to factor in those coin tosses when deciding which properties are best to buy. How would that influence your decision? Well, if you know that you might have some randomness in the decisions you do, you're not going to do something like, decide it's always best to buy blue properties, because you have to factor in the coin tosses. You may not be able to buy blue properties when you want because there might be randomness built in. So you're going to spread out your strategy over, different possible properties that you might buy instead of putting all your eggs in one optimal basket. In opposition, the off-policy concept would be that it's fine if you want to use the random coin tosses for exploration and training, but you actually ignore them when learning the best actions to use against other players. You assume that you're not going to be doing that anymore when you are finished your training, so you can learn optimal actions like always buy the blue set of properties because you don't think some randomness will get in the way of you being able to do that. Now, another way to understand the SARSA versus Q-learning algorithms is to do so mathematically. So we can try that way as well. If you are in the SARSA context on the left here, you're going to select an action using some kind of explorative policy. So again, this is the notation for a stochastic policy. It doesn't always produce the same actions. And you're going to use the action selected using the explorative policy within your Q-learning updates. So this, you can see, is the common format we're used to. We have the new estimate, it's equal to the old estimate, plus some step size, times the TD target. So this is like the same as the concept here is from the Bellman equation. And then you subtract away from the target your old estimate. So note how the values that we're learning are for the action that is actually taken with our explorative policy. Now in contrast with Q-learning on the right here, you still select an action using some kind of explorative policy, but you don't use that action that you just selected, AT plus 1, in your value that you're learning. Instead, you replace that action with the one that the greedy policy would select. So a greedy policy, that would just figure out what is the maximum value for any action and then choose that action. So instead of selecting, AT of 1 and moving forward with that, so the explorative action, you take the max over all the actions available and then move forward with that maximum action that gives you the highest Q value. So it's like you're pretending that you're not doing the exploration and you are learning action values that are related to the best actions that you could select. That's why with the Q-learning context, with the off-policy algorithm, you can, in fact, learn about the optimal strategy, like always buy the blue properties. Over here, you have some randomness baked in. You're updating different action values at different points. So you're going to end up learning about different strategies that you could do. You're not going to learn about a single optimal strategy that you place all your bets on. So I hope that gives you a different view of how SARSA and Q-learning are different. Mathematically, it is just the value update, the action value updates, that makes them different. Lastly, I will show you the difference between these two algorithms when looking at results. Let's say we have a cliff walking task, so it's like a grid world again. The agent has to learn to get from the start to the goal. If it doesn't, then you get a penalty of 0. If it does get over here to the goal, you get a reward of 1. And if you ever, hit any of these boxes which represent a cliff that you can fall off, then you get a reward of minus 100. So, you very much don't want to fall off the cliff. SARSA, because it is incorporating randomness in terms of its strategy, in terms of the action values that it's learning about, it's going to learn to stay away from the cliff edge, even though that this path is longer than the optimal path from the start to the end. If SARSA is learning to take this path, well, it knows that it might sometimes take random actions like, going one step down. And that would be very bad because, you know, the agent would fall off the cliff. So instead, it learns that it should stay a couple of blocks away so that even if there is some randomness, the agent is not going to fall off the cliff. In contrast, we have Q-learning over here, which is going to directly learn the most optimal path because it ignores our random actions. It assumes that we're always going to take the best action, you know, the maximum action value action, which is never going to be the one that, you know, goes to the cliff. So for Q-learning, it can actually take the optimal path, but it's going to be, you know, more risky if you have any randomness. But you're not going to have any randomness after you've done the initial training, you know, the exploration. So that's SARSA versus Q-learning, on policy versus off policy in three different ways. The mathematical way, having these results-oriented analogy, plus the original conceptual definitions. Hopefully that helps you understand the difference between on and off policy, because that's very important. It's going to keep on coming up in all other sorts of domains in RL. SARSA versus Q-learning, these are just two examples of on and off policy algorithms in the TD context. I finally wanted to show you some pseudocode for SARSA versus Q-learning, and hopefully this also helps explain why it's called SARSA. So in our pseudocode, we're initializing some helper info over here. So we have a tabular, you know, Q value system. So we store our Q values in a table where we map state action pairs to some value. Note that we initialize all of these values to 0. So every state and action pair, it maps to a value of 0 at the start. We have a few parameters that we set here. So we have the learning rate alpha that is used in the you know, Q value update. We have an exploration rate epsilon, which is used in an epsilon greedy policy. And we have a discount factor gamma, which is used in selecting the next return. Lastly, we have a map from the states that we're in to a list of possible actions in each state. Then, after we have this bookkeeping info, we need to define a few key parts to our algorithm. We need to define which policy our algorithm will use, and we'll need to define how we will do value estimation that will guide the policy. Finally, we can have a training loop that shows how we go about the RL loop, you know, repeatedly taking an action, then going to the next state and updating our action values as we do so. So we keep doing that. In terms of the policy, we have a simple epsilon greedy policy. So some percent of the time, we return a random action. So that's the exploration part. And for the remainder of the time, we use the argmax to find out what is the highest action value, and we, you know, return that particular action. So that's the exploitation part. The Q-learning update is just the equation we saw on the last slide. So we compute the TD target, which is R plus gamma times QS, and A is, as you can see here, it is the action that the policy is selecting. So that's the key part of the SARSA Python code. We're using the action that's actually selected by the explorative policy. Then we do our update. So our new estimate is our old estimate plus some step size times our target minus the old estimate. Again, this is the general form of fixed point iteration. It's just trying to make QSA closer towards this particular target. Now, why is the algorithm actually called SARSA? Well, if you look at the info that we're passing in, that we're using for the Q-learning update, we're using the state S, the action A, you know, the return R, another state S, and then, you know, the next action determines how we move forward. So these letters spell out SARSA if you write it in a mathematical notation. That's where the name comes from. Now, if we wanted to move from this to the Q-learning context, take a second to pause. What do you think would change? Hopefully you answer that only the TD target changes. So the only change is instead of using an action selected by the explorative policy, we use the best optimal action available. So you can see everything is the same. The only difference is we're no longer passing in the action chosen by the policy because it doesn't matter. We're going to use the greedy action instead. So we figure out what's the best next action that we can take. So we do an argmax over all of the possible actions we can take in the next state, and that is the action that we move forward with. So that's what we use when computing our target, and then we make the same update. So hopefully that gives you some practical pseudocode that you can actually implement if you wanted to try out the SARSA versus Q-learning algorithm. The only difference between the two is the on versus off policy bit, and the thing that makes them both TD algorithms is the way that they compute their target. They're using this TD target where they're using bootstrapping. You know, the estimates for this particular state action pair is being used to update the estimate for another state action pair. Take a pause, try and answer these questions. Okay, assuming you've done so. So what's the key difference between the SARSA and Q-learning updates? It's what we just talked about. SARSA will just use the action chosen by the explorative policy. Q-learning will choose the best action available. So it will use the greedy actions for its target policy because it wants to ignore the randomness because it assumes that we won't be doing the random actions anymore when we are actually deploying the algorithm. Second question, how does the on policy versus off policy affect the policy that we learn, i.e., the behaviors we learn to choose? Well, as in the cliff walking example, when we have an on policy algorithm in general, because it's balancing the exploration and exploitation, it's always factoring in randomness and how we might not be choosing the next optimal action in its decision-making strategy or its policy. Because of that, it will try and be safe. It will be conservative, it will factor in that randomness and not necessarily choose the optimal path. When we have an off-policy algorithm, Q-learning is just one example. It will always focus on the optimal policy, try and learn that, because it doesn't ever consider that it might take in random actions in the process. It ignores that and pretends that just is happening for training, not for the actual end use. With that, take a break and we will continue next with laying some foundations for the actual first modern-ish RL algorithm that we'll learn about. In this next section, we're going to learn about value approximation methods, and to contextualize the problem that this fixes, I'm just going to remind you, in all of the prior methods that we've considered, we always store our action values like this, and also our state values. We have some kind of table, or dictionary, or map, or hash table, whatever you want to call it, where each individual state action pair is mapped to an individual value that we are estimating. If we had state values, we would just have states that are mapped to individual values. But the point is, we have one individual value for every possible, combination that we have. Now, the problem that this has, storing the tables like this in all of the prior methods, which are classified as tabular methods, it's that we can't scale if there are too many states. For example, consider the game of Go. Every possible layout of pieces on the board is a new state, and there are a lot of possible, configurations of pieces on the board. So there's no way to store that many, state values or action values where we store individual numbers for each value that we're trying to estimate. Similarly, if we have too many actions, for instance, we have continuous actions like controlling the angle of a robot motor. Well, the angle can be any real number, so not quite any real number, but even still, it can be infinitely many possible numbers. So there's no way to store all of those, you know, individual action values, as in for each individual action, in memory in a table. Similarly, when we have high dimensional states, for instance, consider an image where we have like megapixels, 10 to the 6 pixels. Each of those individual pixels has, let's say for now, scalar values. That's going to result in a lot of possible combinations of scalar values. So again, you'd have too many states. So in all of these types of problems where you have just a lot of different states, you have very high dimensional states, you have, let's say, continuous actions or way too many actions, we cannot store a table that is going to just be in memory and map individual state action pairs to values. So in these contexts, we need value approximation. Value approximation, the way that it solves this problem is by representing values as functions instead of individual values being stored in a table. So these functions have, parameters that we can learn, and we change the parameters such that the functions give us whatever, um, whatever state or action values we want. So we'll use optimization algorithms to change these parameters. For one example, gradient descent, which I'll introduce later. To give you a concrete example of what I mean by having functions with learnable parameters, for instance, we could have our action value function be something like this. Before we had QS of A, as in the stated action are two inputs. Now we have QS of A parameterized by phi. So this colon, semicolon, and then this variable, that means the function is parameterized by. So this parameter is going to be some number that we select. So it can be like 3.2 or 5.7, whatever we want. But it's not going to change across all of the inputs. The inputs can change. The parameters is whatever we selected. So for instance, if we had a linear approximation, that type of function, we would have a linear multiplication between the parameters and some function f of the state and action values that we were passed in. As another example, take a parameterized state value function, but now in the context of deep reinforcement learning. Now we will use an AI algorithm like a neural network as our function. So we pass in the input state we got, we pass in the parameter phi, and then the neural network will return some state value. For our purposes, in all of this presentation, I won't ever go into the details of how algorithms like neural networks work, because all we care about is that they are some parameterized function. The general idea is that we're not storing a value per state action pair as we were in the prior pseudocode. Instead, we just store the parameters, so phi in these contexts, and then we compute the values as needed for every state and action that we encounter. Now, I mentioned this optimization algorithm, gradient descent. Let me just dive into the key problem that it's trying to solve. So we'll work in one dimension right now, just consider scalar values, though this also extends to multiple dimensions. Let's say we have this simple linear approximation function. So we have the state value of s parameterized by phi is just equal to the parameter multiplied by the state value. And both of these things are real numbers. What we want to do is figure out how we choose phi so that we get, good state values that are, approximating what we want. The first ingredient we need in this process of optimizing the parameter phi in order to do what we want is we will need a loss function. A loss function which will measure how close our parameterized state value is to the true state value that we want. We'll look into, how do we get this true value later on. For now, let's just say we have it. One particular loss function we can use is the mean squared error loss function. We can, work backwards. The error is this term right here, so it finds the difference between our parameterized function and the true values that we expect for that state. This could be positive or negative, but an error of -5 doesn't make sense in this context. So we square that error so that all the numbers are positive. And finally, we take the mean. So add up the errors across all of the states S and then divide by the number of states S. This is what this notation here means. It means the number of states S. So once we have a loss function, we will know, let's say we picked, phi equals 3.2, we will be able to tell whether or not that is a good value to pick for our parameter, depending on whether the loss function is high or not. For instance, if we wanted to compare phi equals 3.2 versus 3.3, we could plug it into this equation, and then we would know, which option is better based on which has a lower loss. The problem is that, there are infinitely many possible values for phi that we could choose. So it doesn't make sense to just do trial and error, pick different values for phi and see what happens. So for now, let's assume that we know, this true value and figure out what we can do better to proceed in an automated fashion, not individually pick as humans different options for what this parameter could be, but create an algorithm, namely gradient descent, that can pick the best options for us. So I'll explain gradient descent first to you visually. There's a bunch of info on screen. Let me walk you through it step by step. Let's start by focusing on all of the things in black. So we have a graph here. On the y-axis, we have a loss function, so L of phi, and on the x-axis, we have different values for phi. So what we want to do is use an algorithm called gradient descent to minimize the loss. We want the values of phi to be picked such that they're approximately right here, because this is the minimum loss we can achieve on this graph. The way we're going to do this is use this key equation right here. Now, this equation might look bizarre. So it's saying, okay, if we want to minimize the loss, the way that we do that, so the way we pick a good value of phi to minimize the loss is take the old value and subtract away the derivative scaled by some step size. And you might think, well, where did the derivative come from? Like, what does the derivative have to do with anything? So the first thing that I'll mention is, why the derivative is relevant. Let's say we currently have a value of phi that is this blue dot, so it's approximately, 5. We can compute the derivative of the loss function with respect to phi at this point, and the derivative is just, the slope of the tangent line. We see that we get this derivative, and the slope is positive, so the derivative is positive. Now, if we perform the update in this equation here, so we have phi is about 5, and we subtract away the positive derivative scaled by, let's say, alpha, we can set it to 1 for now. Well, 5 minus a positive derivative, that's going to be some lower number. So we can see that phi, it will get smaller and go closer towards the optimal value that we want. Let's consider this red case here second. So now we have, let's say phi, it has a value of 2. We compute the derivative of the loss function with respect to phi at this point, and we get a negative derivative. Well, if we take phi, which is 2, again we assume the step size alpha is 1. So take phi and then subtract away some negative number. Well, subtracting a negative number, that's the same as adding. So phi will get bigger, and it will move closer in this direction, closer towards the optimum point. So we keep repeating this equation. What I'm showing you is no matter whether phi needs to get bigger or smaller, this equation in gradient descent, it will make phi move in the right direction, such as to minimize the function. So that's the visual intuition behind gradient descent. You might be wondering, what is this thing gradient? What does it mean? A gradient is just the generalized term for a derivative. So a derivative is just for a single scalar number. The gradient extends that to multiple dimensions. So this can be said, negative gradient, positive gradient. So that's why it's called gradient descent. We're trying to descend to the lowest value in the function by using the gradients, aka the derivatives. Now I'm going to write this out mathematically. So here is our loss function, and here is the gradient descent equation, where I just, change the notation to extend to the general higher dimensional case. So this symbol right here, this is called nabla. So nabla sub phi is just the same thing as writing, d by d phi. So this is just the general notation for a derivative, which we call a gradient. Again, you can see that it fits into the scheme over here that we expect from fixed point iteration. The new estimate, so the new phi, is the old estimate plus or minus the step size multiplied by the target. And the target over here is this yonder, this estimate minus the old estimate. So we're just using similar ideas with fixed point iteration in yet another context, as we keep seeing throughout all of reinforcement learning. Now, the only question remaining, so we answered the question of, okay, we have a way of figuring out if we currently have a good parameter phi or not with the loss function. We also figured out how to automatically update the parameter phi without us picking like, oh, let's say 3.2, let's say 3.3, let's just see what's good. Now we have an automatic way of using this optimization algorithm, gradient descent, to reduce this loss and make our state value function closer towards the true values that we expect. The only question remaining is, what are these true values? If we don't know what they are, that's the point of estimating this approximated value function. If we already knew the true values, then we wouldn't need this function in any case. So now we have to define what this is in a way that is pragmatic. So the way that we're going to do it, if we had, supervised learning, we talked about this earlier, this is, how most AI algorithms work. We would have humans sit down and, figure out what are the true values. For instance, if you want the value of state S1, some human sits down and says that the value is 10. If that doesn't make sense, well, we can't do that, obviously. Like, humans can't estimate the right way to solve the problem in RL because we don't know what the correct answers are in reinforcement learning. That's what it's all about, trial and error and learning as you go. In supervised learning, just, annotating some human labels is fine. You can say, this image is of a cat, that image is of a dog. But in RL, we don't have correct answers, so we do not have true values. Instead of having these annotated labels then, what we do is we use bootstrapping as we introduced in the TD method section. We're going to use the prior estimates of our state value function as part of the targets. So for instance, we can use the TD target from earlier. So we can say that this TD target, the current reward, plus a discount factor times the reward at the next state, it's approximately equal to the true value. So again, this is using bootstrapping, where we're using our estimates for the state value at state st plus 1 in order to improve our estimate for the state value at state st. Then we can use this TD targets in our loss function. So this is the mean square error loss. And finally, we apply gradient descent. So this gives us a practical algorithm that we can apply. We can recreate these equations in order to use value approximation instead of tabular methods when trying to estimate the state value function. The only problem to note here is that, well, the true values, when we're saying something is true, well, every time we change the parameters phi with gradient descent, note that the true values, they're dependent on this parameterized function, which relies on phi. So we change phi, that changes the true values, which changes phi, which changes the true values. So this is often problematic. There are no theoretical guarantees that we can converge on some fixed solution in this way of using value approximation. This problem doesn't exist in supervised learning because the true values are, fixed labels that humans wrote up. This is why reinforcement learning is often a more difficult problem to solve than in supervised learning algorithms. Now, the only thing I want to define besides this is to do this with action values instead of just state values. So we basically do the same idea. Our TD bootstrapped target for Q-learning is just going to be this. So we use this equation in Q-learning. The only change is now we have parameterized Q functions over here. We use that in the mean square error loss. This term here means, we're averaging over the number of states and actions. So if there are like 10 states and 10 actions, then we divide by 100. That's what this term over here means. So we'd compute the error, square it, and then take the mean across all the states and actions. And we'd get the mean square error again. Finally, here's our gradient descent equation as usual. So now that we've defined the equations for value approximation in the state value and action value context, let me show you a version of Q-learning with approximation instead of, tabular methods. So now I'm going to use this neural network, which is some, fancy function, and it will do Q-value approximation. We have some parameters for the new neural network, which we will call phi, and we need to optimize them with gradient descent. Here is our step size, which is also called a learning rate in the context of gradient descent. And this is our discount factor gamma. So we have the same Q-learning update as usual, where we figure out what the next best action is by sending in the state and action values for different actions. We send it into this neural network now, which uses the parameters phi in order to return the action values. Now, I forgot to add this thing here. So actions at each state, let's just say that's a list of actions that is available to us. Then we just go on as usual. So we compute our TD targets, we compute the mean square error loss, where we compute the difference between the target and what we're currently estimating given our parameters. and square it and so on. Then we compute the gradients, so the derivative that we need. There's an algorithm that you can look up called backpropagation, which is useful to compute the derivative of the loss with respect to phi, so the parameter of q. And finally, we do our gradient descent update. So the new value is equal to the old value minus alpha times the gradient. Also, just for variety's sake, instead of having an epsilon greedy policy, you could do that. I just implemented a softmax policy instead. So I compute the Q values for all of the actions in the current state. Then I exponentiate each of them, and I compute uh, the value that we have divided by the sum of all the values for each of the softmax probabilities to be computed. And finally, we have our training loop. As usual, pick some initial states. The action is going to be sampled from the probability distribution returned here. And then we move on to the next step by taking that action in the environment. We do our Q-learning updates, which, goes and does all that here to update our parameter phi so that we can get a better estimate of the action values next time. And then we go on to the next step and keep repeating this part. So with all that said, quickly pause here to check your understanding of value approximation. And now let's go through the questions. So when do you need to use parameterized value functions or approximated value functions? It's when you have too many states or too many actions. So this can occur when you have, for example, continuous actions that you need to take, like controlling a robot's angle. Or you might use this when you have way too many states in the problem that you're trying to solve. For instance, a game of Go, or doing something with an input that's an image. What makes parameterized value functions harder to learn than tables? Well, remember what we mentioned. The first thing is that when you change the parameters with gradient descent, the state values also change, or the action values also change. So it's hard to find a stable algorithm because of this, because any change you make, it changes the true values or the estimates of the true values that you're working towards. The other thing that I'll mention is that you have one set of parameters that you're using to compute each and every action value or state value. And this means that your parameters have to be good in general. They have to work across all of the different states and actions that you might receive. With the tables, if you noted down, the value for state 1, action 10 is 5, and that's not a very good estimate, whatever. It doesn't boil over to affect all the other estimates. But in this parameterized case, if the parameters phi that you pick are no good, well, they're no good. You can't really limit the impact of that. It's going to affect every single action and state value. And finally, what makes gradient descent more tricky in RL than in supervised learning? As we just said, in supervised learning, the targets that we're working towards are fixed. In RL, every step of gradient descent changes the parameters phi, and that changes the target that we're working towards, which creates instability. With that, we're done with value approximation methods, and when you check back in next, we're actually going to learn about our very first modern RL algorithm. And when I say modern, like 2013, but whatever, it's still a lot more modern than everything else we've been covering. Okay, now we're at this very cool section where we get to learn about a practical RL algorithm. This is called the Deep Q Network, or DQN algorithm, and it came out in around 2013, 2014. The main use case for DQN was that the authors wanted to use it to automatically learn how to play these old Atari console games. So you can see here we have Breakout and Pong, Space Invaders, and Sequest, and so on and so on. Maybe you might have seen some of these games at some point in life. But the way that the authors wanted to do it was they didn't want to define, game-specific rules. They just wanted to give the agents an image of the screen in each of these games and then just let the algorithms figure it out from there. So that's what they did. They managed to achieve two key innovations with this algorithm, which is one, they were able to go directly from raw pixel frames, so, images of the game screen, to actually estimating Q values. And two, they were able to use what we call experience replay, which is a mechanism to make sure that these algorithms don't get stuck in local optima that work now but won't work, maybe a few seconds from now as the game changes. Let's dive into the details. So the first challenge that DQN had to solve is that there was a lot of information in the input that it was receiving, which were these raw pixel frames. It didn't get things like, here's the position of, the character in Pong, or here are the, enemies in Space Invader. It just got the raw image. So there were 84 by 84 pixels per, frame, and we have grayscale images, so each of these pixels just has one number associated with it. And then we had a stack of 4 frames that were all fed into the model together so that you could capture some motion. Here's what's changing between the different frames. This results in millions of different combinations of possible pixel states across these 84 by 84 by 4 frames that the model receives in every single input. So they needed a model called a convolutional neural network, a CNN, in order to effectively downsample all this data and condense it, not get stuck in all of this detail, actually summarize the information, condense it down. For the sake of our RL tutorial again, we can treat the CNN as just like black boxes or functions that do something. And we just care about, we send in this input, we get this output. Now here's the architecture of the DQN. So you have those 84 by 84 by 4 frames. They are grayscale, unlike in this nice image. We pass it through a CNN, which is just some image processing function for our purposes, and it will output a action value for each state and action pair. So we assume we send in some state information. So this is the current state. This 84 by 84 by 4 matrix is the state, and we will output an action value for every possible action in that state. Now, keep in mind the benefits and drawbacks of this type of output. We can compute all of the Q values for every action that's possible in that state all at once, which is, well, it's efficient. It's better than, passing in one action at a time and getting one action value at a time in terms of computational effort. But the problem is that it only works for discrete actions. So if you just have, WASD controls in a game like Pong, if you can just move up, down, left, right, or you have some discrete number of actions, this is fine. But if you have infinitely many actions, like let's say you want to control a robot's motor, this is not going to work anymore. The next problem that we have to fix in order to learn effectively is that when we're passing in these 4 frames of an image, these are going to be very correlated. And not just, 4 frames, but like as you progress across each time step, you send 4 frames at a time. So the first 4 frames are correlated, the next 4 frames are correlated, the next 4 frames are correlated, and so on and so on. So barely anything is changing across pixels, as you can see in these 2 frames here. Like you can see over here, if we go from left to right, looks like the green paddle has moved down, the ball has moved further in this left direction, and the orange paddle seems like a little bit lower, but not that much lower. But like, what do you do with that? What does the model learn? Maybe it learns, okay, if the ball is going this way and it's going down a bit, like maybe it'll bounce and then like come back. I don't precisely know, how much it's gonna bounce. So maybe I just, if I'm controlling the orange paddle, like I just stay there, maybe I move it up a little bit. So it gets stuck in the local optima of like, what do I do right now? It can't learn generalized patterns very well if we just presented these sequential frames that are just all correlated with each other. To solve this problem, the authors proposed a solution called experience replay. This is where we store past experiences that we've had in memory. So we say, okay, like the past 10 time steps, not 10, more like 100,000 or so on, but a past very many number of time steps are going to be stored in memory in this replay buffer. And then we're going to sample random batches on random batches from this replay buffer. So random groups of experiences across all of the things experienced, and we're going to train on them in between us actually taking actions. So while the game has been given an action and it's passing time waiting to render the next frame, in the background we're going to start planning on, hey, here's what we learned from the past, how can we reuse that experience to get our action values better. And the benefit of this is that we're interrupting each, sequential correlated frame with random batches of data that we've experienced at different moments in the past, so that we're not just, hyper-focused on what's going on right now. We're reviewing our old lessons learned as well. Here's a, step-by-step kind of description of how to do this. So let's say we're going to store up to 1 million data points. That's the size of a replay buffer. Each data point will store the state that we had, the action that we took, the reward that we got, and the next state that we ended up in. So we sample a batch, let's say a batch of B elements, so B data points from this replay buffer, and then we're going to run Q-learning updates. So we're going to have the same, value approximation equation that we introduced in the last section. And then what we're going to do is just compute the loss averaged across every single data point from the batch that we just drew out of the replay buffer. So this is again mean square error, where the mean is happening over the B data points that we drew from the replay buffer. And this notation over here just means like each of these data points is part of the batch of B data points that we just took. We do that, and then we can run gradient descent in order to update our parameter values. Now, why is this useful? Once again, we can do it in the background. Before the game is ready to render the next frame, we can run this computation really fast and review lessons we learned in the past instead of just being hyper-focused on the present moment. So here's the pseudocode version of the full DQN algorithm. I'm no longer going to present Python pseudocode because, it's going to get longer and longer. So we're going to look at pseudocode in this format instead. Let's just zoom in. So at the start, what are we doing? We're initializing our replay buffer. So we call that D, and it can store up to n samples. In the paper, they used 1 million. And we initialize our action value function Q with some random parameters. So weights is a synonym for parameters in this context. The parameters are in this paper, they're labeled data instead of feet. Over here, we're going through different episodes of the game. So remember, the game, eventually will end. Like let's say in Pong, if you run out of lives, the game ends. Or, in the breakout game, if you run out of lives or you run out of bricks, the game ends. So for each episode, we're going to initialize some, trajectory or sequence, and we're going to pre-process some data. So this is just pre-processing the image. They just take the raw image from the game, and then they will downsample it. So they will crop it down to 84 by 84 pixels. They will convert it from red, green, blue, so colored game screens, to just black and white pixels, and then they will stack 4 pixels together. That's what this function phi does. And yes, it's unfortunate that they use parameters data, and phi is now a image preprocessing function, but what can you do? So now for each step in this episode, so from 1 to t, that's the terminal state, you're going to use the epsilon greedy policy to select a action. So epsilon percent of the time, you're selecting a random action, otherwise you're selecting the greedy action using your parameterized values. So phi of s, that's just, the preprocessed image, and that is the state, that's the input that the algorithm gets. A is the action that is possible to take. So maybe you can move up, down, left, right. And then theta are the parameters. You choose the best action out of the possible action values. You run that action in the game simulator, and then you get the reward and the next image. And this image, again, it needs to be pre-processed. So you group the state in here and start pre-processing. Here's the black and white 84 by 84 pixel by 4 stacked frames version of the image that we just got. Now for the experience replay part. So we're done interacting with the simulator for the current time step. Now we're going to bring in experience replay. So we store the transition that just happened. We just store, the event that just occurred in the replay buffer. And then we start sampling a random batch of transitions from D. So we, sample a bunch of transitions like this from the replay buffer. This is just, computing the reward as we saw. So over here, this is just a fancy way of saying compute the TD targets that we saw earlier. The only reason for this case statement is if the state that we're in is terminal, then there is no, future value, because like there are no more episodes. So we just have RJ plus 0. If the state isn't terminal, then we use the normal TD equation, the TD target that we're used to. So we call the target y of j in this case, and we perform a gradient descent step on the square area here. It references equation 3, that's just the gradient descent equation that we showed right here. So anyways, that is the pseudocode for DQN. One thing I did want to point out, note that we're using an epsilon greedy policy that involves this, maximum term. This is one of the reasons why DQN doesn't work for continuous actions. Because if we had infinitely many actions here, we couldn't, go and sample each and every action to figure out which one gives us the maximum action value. So we'll need to adjust this algorithm. DQN can't currently work for continuous actions. We'll come back to this in the future and talk about other modern RL algorithms that fix this problem. Finally, let's look at the results of DQN. So just be warned, I have used a log scale here because in some cases, humans are like still 10 times better. So these yellow bars are human. They're still 10 times better than all of the other algorithms. We have DQN, as you can see here, in red, and some other things that DQN was compared to. So usually you can see that humans are best, except in a couple of cases. So in simpler games like Breakout, Enduro, and Pong, then the DQN is actually, at least a little bit better than human performance and also all the other algorithms. In most of the games, though, so the more tricky games like, let's say Cuba, Sequest, Space Invaders, stuff like that, when you see like a, 10x difference here, the human might have like a score of like, let's say 20,000, while all the other algorithms are like 2,000 or below. So there's still, good room for improvement in this algorithm. But in all of the cases, it outperforms, it is the state of the art in terms of other RL algorithms that it was compared to. So this was very, very good. This was one of the first times that we had actually, an RL algorithm exceeding human performance in some great games, and doing so when directly given the frames. It was not trained on hand-engineered features. It just was set in one way, given frames across different games, and it learned what to do in each game without being reprogrammed. So this was pretty good. If you want to pause to check your understanding for DQN, do so now, and then we'll take up these questions. So first, why is using raw pixel frames as states challenging for reinforcement learning? Well, if you have to parse all of that information, you have all of those state combinations, you have a bunch of information being thrown at you, and somehow out of that, you have to extract the key details you need to make decisions. That's going to make the, problem more challenging. What are some benefits and drawbacks of experience replay? This concept is going to come up again and again. So lots of modern RL algorithms use experience replay, and some they use alternatives to it in order to get around its drawbacks. So the benefits are that we can decorrelate sequential frames. We can do some background planning where we go review what we learned in the past instead of just, optimizing for what we're seeing right now, hyper-focused. The drawbacks is that one, we require a lot more memory because, we're storing all of these past transitions in our replay buffer. And two, we actually are restricted to using off-policy algorithms like Q-learning alone. This is a subtle point that many people miss, so let me point it out. When we are when we are using experience replay, we're storing, here is our current state, here's the action we took, the reward we got, and the next state. But this action was generated by some policy, that had some parameter value data. The problem is, when we store this transition into the replay buffer, afterwards, what we're doing is we're doing gradient descent. So we're changing the parameters data. So on the next step, we'll have a new parameter data and we'll pick a new action and then, again and again. So these transitions that are stored in the replay buffer, they're generated with old versions of the parameter data. And that's akin to having old policies that generated these transitions. And then we use those old transitions generated from old policies to do the updates. So this means that we do not have a single on-policy algorithm because we can't have a single version of the parameters that are used to generate all of these transitions. Data is always changing. So because of this, experience replay always makes an algorithm off policy. It always means that we will have multiple versions of policies that are being used in the value updates and being used to select actions. All right, next, why can't DQN be used for continuous action spaces? Well, the main reason is the argmax term that you saw. So because we're using an epsilon greedy policy here, we need to perform a max when we are in the greedy portion. And if there are infinitely many actions possible in a continuous setting, then we can't do this. We can't try out every single action out of infinite possibilities. So we'd need to make some changes in order to use DQN for continuous actions. And finally, why can't DQN be used for on-policy algorithms is because of this experience replay point that I just explained. With that, I hope you found that cool. That was our first modern RL algorithm. Next up, we're going to talk about another set of techniques that will motivate the remaining, I think, 4 modern RL algorithms that we'll discuss. Before we get into the formal policy approximation details, I just want to introduce an optimization algorithm we'll be using in this section. If you recall with gradient descent, I explained it to you visually, where I gave this example showing how this update equation right here, it can change the parameter values phi so that they become closer towards the local minima. That is the local minima of this function L of phi. So gradient descent will minimize functions that we apply it to. In contrast, we have a variant, which we call gradient ascent. It simply maximizes the functions we apply it to. The only change between gradient descent and gradient ascent is that this equation has a sign flip from this negative to a positive sign right here. So let's just pretend that this is a positive sign for the rest of this example. Now, let's say we're at this blue parameter phi, which is a value of 5, and then we add on some positive step size alpha multiplied by, as we can see, a positive derivative here. Well, that's going to make phi increase because it's 5 plus positive times positive. And if phi is increasing, well, it's moving closer towards the local maximum. In contrast over here, we have this red point, so phi is about 2. It has a negative derivative. So 2 plus a positive value times a negative value. Overall, we have 2 plus a negative value. So phi will decrease. It will go this way, closer towards the local optimum, which is less than 2. As we can see, if we simply replace this plus sign, a minus sign here with a plus sign, we change gradient descent into gradient ascent and now can maximize functions instead of minimizing them. With that aside, let's dive into policy approximation, which is a pretty natural extension to value approximation techniques like DQN. So DQN, it uses gradient descent in order to figure out what are the best parameters phi for this parameterized or approximated value function. Now, this means that we don't have to store a bunch of Q values in a table somewhere in memory. We just store the parameters phi, and we can compute the action values that we want whenever we need them. Policy approximation, well, it just asks the question, hey, what if we applied this parameterization or approximation to the policy function as well? So if we directly parameterize the policy with some parameters theta, what if we could just, do that and then use some optimization algorithm in order to pick the best values for theta that will give us the actions that we want to select? The function that we parameterize with, it could be a simple linear function, or it could be a neural network, which for our purposes is just a fancy function that takes in whatever the input is and the parameter, and will return the probabilities that we're looking for. The first immediate benefit of this is that it will work for continuous actions, unlike DQN. With DQN, we had an epsilon greedy policy, and the epsilon greedy policy involves this term, where we argmax over actions. If there are infinitely many actions, because let's say, you're controlling a robot and it has a motor that you can adjust to various angles, there are infinitely many possible angles. And so we would have to argmax over infinitely many possible actions to figure out the best action out of them all. We don't have to do that here. We don't care what the number of actions is. None of these formulas involve any terms that are dependent on the number of actions. We just compute this function the same way for whatever actions we're interested in, and based on that, we can proceed. So now we are able to support continuous actions with parameterized policies like this. Note that we can just use the parameterized policies alone because, if we can just change the parameters in order to change our policy, we don't need this two-step process of having the value functions and then figuring out the policy based on that. And that's what we will do in this section. But we don't need to do things that way. We can have parameterized value functions and policies, which we will cover in later sections. So the key idea to take away, now we just have a parameter for our policy, and we have to figure out the best value for this parameter to get the best policy. Now, what does best mean? The thing that we want to define is something that we can maximize or minimize in order to get the best parameters. One candidate is, hey, we're trying to get policies in order to get good returns, rewards over time. So why don't we just maximize the expected return from following the policy that we have? In formal math words, instead of English, we can write it this way, as this expectation, where tau is, a trajectory that eventually will end. So what do we mean by this notation? Well, the thing that we're trying to maximize is the expected return. So this is the discounted reward. Now, this will depend on the trajectory that we have, because the trajectory will define the rewards we get. And the trajectory is based on our policy. So our policy will pick, actions A0, A1, and so on, which influences the rewards we get. So that's why we say that this is a function of data, is a function of the parameters. As we change data, as we change the parameter, we change the policy, which changes the trajectory, which changes the return that we get. So we want to change data in a way that maximizes the return we get. Now we can use gradient ascent instead of descent, as I just introduced earlier. The only change we have is this negative sign becomes a positive sign. Typically, I'd leave it here. I'd just say, here's the target function that we're maximizing, and here's the gradient ascent equation to maximize it. The only problem is that if we're trying to compute this gradient, this is going to be actually very difficult. The reason is that data is involved within the probability distribution that we're sampling from. The trajectories are based on data. As data changes, the trajectories change. Now this will make this computation on this formula very difficult. So we actually need something called the policy gradient theorem to make this computation feasible. Now, I'm going to be honest, this is going to be the most involved proof that we're going to do for this theorem. So if you want to skip it, you already know the key ideas. Here's what we're maximizing. Here's the equation we're using. The next two slides is just a kind of annoying proof to rewrite this in a format that is more computable when we dive into it. So let's start here. We want to compute this gradient for this expected value, as we just defined on the last slide. I'm going to expand this expected value with the expected value formula, which we introduced earlier. So we're summing over all the possible trajectories, and we're going to compute the probability of each trajectory multiplied by the value, the return that we'd get for that trajectory. Now we can apply the derivative sum rule. So the derivative of a sum is the sum of the derivative. So we just exchange these two operators. Note here that g of t, the return, it doesn't at all depend on data. It's just dependent on these terms right here. So the discount factor and the rewards we get. So because it doesn't depend on data, we're going to factor it out as a constant. Now we need to break up this term into something more, low level, let's say. So we're going to expand this probability gradient right here. The first thing that we're going to do is we're going to apply a log derivative trick, which is it's a byproduct of the log derivative rule. So if I asked you what the derivative of ln of f of x is, you'd apply the chain rule. It's 1 over f of x multiplied by the derivative of f of x. If we just rearrange this formula by multiplying by f of x on both sides, we get this. The derivative of some function is that function multiplied by the derivative of the log of that function. If we rewrite this in multivariable notation, we replace the d by dx with these gradient symbols. We're still differentiating with respect to x. Now, if you look at this and you look at this, well, these two things look very similar. We have f, that function, now being this p function, the probability of the trajectory, and theta is replacing this value x. So if we just apply this equation right here, we can expand such that we have this expression over here, which looks a little bit messy. The good thing, though, is that we have the sum over probabilities. So if we just rewrite this a bit, we can move the probabilities over here, sum over probabilities, and we're multiplying by these values. I don't know about you, but that sure looks like a, expected value to me. So I can rewrite it as an expected value. But now, note one thing, the gradient, it's not over all of the probabilities, it has been moved over to the inside over here, which is going to make our computation more tractable. So continue here. So I need to now figure out what this gradient of the log of the probabilities is, which, we can call grad log prob, as you'll see later. I'm just going to create a new slide. So I'm going to copy this equation over. So here's that exact same equation right here. I haven't made any changes. Now we need to figure out what this inside term here is. To do that, I need to define what the probability of an entire trajectory is. So a probability for the entire trajectory is just going to be the probability of each individual section of that trajectory, let's say. So the probability of each state and each action occurring along that trajectory. So we have the probability of the starting state, which is determined by the environment, and then we multiply onwards the probabilities of choosing each action given the prior state we were in, and the probability of getting each next state given the prior state and actions. This pi notation, it's like the summation notation, but for multiplication. So whereas the sigma notation, it assigns this value and then computes an expression and then increments this until we get to here and sums everything up at the end. This does the same thing, but we take the product of all these terms. So we have t equals 0, compute this, t equals 1, compute this, t equals 2, and so on, and then multiply everything together at the end. Now, we want to go closer towards, what is the derivative of the ln of this expression. So we're going to take the ln on both sides. Here we can apply the log multiplication rule. So we take the ln of all of these multiplied terms, well, they all convert into individual ln terms being added together. So we have the ln of this thing right here, plus the multiplications turn into additions, and ln of these two things multiplied is ln of the first plus ln of the second. Why did I write things out this way? Because now I can actually take the derivative that I'm looking to, aka the gradient in multivariable terminology. So if I take the gradient on both sides with respect to theta, clearly this thing is not, dependent on theta. It doesn't have theta in it. Neither does this thing right here. It's only this term over here which involves theta. So these two become 0, and we're only left with this thing right here. Now that we know what this thing is, we can sub it back into the equation at the top. So I just do that over here, and that is our policy gradient theorem. We can use it with gradient ascent. So we compute this derivative, which involves the policy, which is a parameterized function. No problem taking the derivative of that, because we can control the function that's here. It could even just be a simple linear function. And after we've computed the gradient, we just use gradient ascent. Now, let me just show you some pseudocode to implement these two key equations right here. So we can do so with an algorithm which we call the reinforce algorithm. The key thing about this algorithm is it does not have any value functions. It just has the policy, which is parameterized, and it has gradient ascent in order to improve the parameters such that we get a better policy. So our policy will be a neural network with parameters theta. This is our step size for gradient ascent. Now, each time we iterate on this policy, what we're going to do is we're going to generate an episode. So we're going to run the policy, get a terminal trajectory, aka an episode. And for each time step in that episode, we're going to compute the return, compute the grad log pi thing I just said. So take the gradient of the log of the policy, and then apply it to the gradient ascent equation. So these are just the last two equations that you saw on the previous slide. That's it. Very simple. And with reinforce, now we can start doing continuous tasks. For instance, we could control the thrust of a rocket, which direction it's thrusting in, how much thrust there is. We can approach continuous tasks like this. Overall, the pros of the reinforce algorithm is that one, we don't need to learn value functions. So as you saw in the pseudocode, it was very simple. But moreover, the computations are reduced because we only are learning one function, the parameterized policy. The other thing is that it works for continuous actions, which DQN didn't. What are the cons of this? Well, the first thing is that we have sample inefficiency. So we need to generate an entire trajectory, and then we go about and do our updates. As you saw in the pseudocode here, generate an entire trajectory, then start doing the updates. Then, new trajectory, then start doing the updates. This is very sample inefficient. Prior algorithms that we saw, often they would make updates, one step at a time. And as in the case of DQN, we could have experience replay where we stored past samples that we could learn further from instead of relying on continuously getting new samples. The other problem is that reinforce tends to be unstable. Now, let me give you a few intuitions as to why. The first, let's actually go in reverse. So the first thing is that the return that we're generating, G of t, it can vary a lot from episode to episode. So this thing, it can vary a lot each time we, create a new trajectory. And that can make our updates go in a lot of different directions. Because if G of t is big, then we might have a big update on that one episode, but then next time, let's say G of t is much smaller, then we have a different update, so that adds instability. The next source of instability is that we have a harder problem in general, because intuitively, when we have the DQN algorithm, first we learn the values, and then we derive a policy from them. This is like single tasking, doing one thing at a time well. Now with reinforce, we're trying to do everything all at once. We don't have value functions. The parameters theta have to be updated in a way that both helps us figure out which actions are good and helps us select actions. So that's a harder problem to solve. Next, we have highly correlated samples because there is no experience replay. We're just seeing what's going on in the environment right now and optimizing for it. And in the example of, let's say, the rocket, let's say, we're about to land, the agent might learn, okay, minimize our velocity as much as possible. But that policy clearly won't work when we're trying to take off. So we might have highly correlated samples that incentivize us to focus on just the current environment, hyper-optimized to it. And that can cause problems. The last thing, which is a bit of a technical point, usually when we use gradient descent or ascent, we want to, use it on a fixed function, like in the rest of supervised AI. The problem here is that whenever we compute the gradients in reinforce, it changes the function that we're actually computing it on. Let me show this to you here. So in these last two equations, let's say we just computed this gradient. Well, as soon as we use it to update the parameters theta, Well, GF data has changed because data just changed. So we compute the gradient, make the update, and now the function that we're computing the gradient of has changed because of this term, which depends on data. So every time we make an update, we're going in a slightly new, different direction, which makes the algorithm actually have no convergence guarantees in general. When I say that, I mean it can keep on going forever, just, moving the parameters in slightly different directions. With all that said, take a quick pause and try and answer these questions. Okay, so first, what are the benefits of directly parameterizing the policy? One benefit, as we just saw, was we were now able to have continuous action support. The other benefit was that we don't have to compute value functions, which can save us computational or memory resources, as we're not storing any approximated or tabular value function. The other thing is, why do parameterized policies make RL less stable than tabular policies? Well, for all of the reasons we just mentioned. It's a harder task. The actual updates, they change the function that we're targeting, and that can make for a lack of convergence. Now, all of these are big problems which make reinforce actually kind of not that great in terms of performance. So now we're going to look at some modern RL algorithms in the next section, which offer different modifications and solutions to the problems we presented here. Take a pause, and I'll see you in the next section. From here on, we're done our theoretical exploration, and now we'll only explore modern RL algorithms that use the same building blocks in different ways to produce more and more effective results. The analogy I like to give is based on this conversation I had with a zoologist. When I looked at a bunch of different animal skeletons, I was very curious. I asked this one zoologist what they saw that made these things interesting. And what they said was that for most people, all these skeletons look very different, but to a trained zoologist, the skeletons are actually rather similar. They just have the same elements that are being repurposed in different ways so that these animals can specialize in different niches. Now, in RL, we have the same exact situation. We have different building blocks that we've learned about, and we'll leverage them in different ways so that the RL algorithms we learn about can occupy different niches. They can fulfill different uses to varying degrees. The first algorithm that we're going to learn about is called Deep Deterministic Policy Gradient, or DDPG. It specializes in continuous actions, unlike DQN, but it takes some of the limitations of reinforce that we saw and improves upon them. It can solve continuous action tasks like this, let's say playing a game of ping pong, where you need to figure out how precisely to move your paddle. Now, DQN and reinforce are the two algorithms that are the foundation of the techniques used in DDPG. In DQN, the main challenge to be solved was for discrete actions. The policy used was Epsilon greedy with an argmax term that didn't support continuous actions, like, let's say, this robotics example of precise motor movements. With reinforce, we had policy approximation that did enable continuous actions, but the algorithm was sample inefficient because it needed many episodes to learn, and it was unstable due to multiple factors like a loss function that is changing with every update and a correlated sequence of updates that can lead to local minimization or maximization. Now, DDPG, it takes inspiration from these two algorithms and tries to combine the best features of each. So here are a few of the key innovations with DDPG. The first thing is that we have what we will call an actor-critic architecture. What that means is we will have an architecture where there are two separate components, one that focuses on learning value functions, that's the critic, and one that focuses on learning the policy, that's the actor. So the actor will learn a deterministic parameterized policy, so mu of s parameterized by theta, which outputs continuous actions. Let's say, it can be between 0 and 1, or between -1 and +1 to move a motor in a certain direction. The critic, it has a separate, also parameterized value function, q of SA parameterized by phi, and that has the responsibility of learning which actions are good to take. It incorporates the same experience replay mechanism that we saw in DQN, which means that we store past experiences that were encountered and then reuse them for further updates, essentially learning more from them and also decorrelating the sequence of experiences that we're learning from to prevent local optimization. And finally, to ensure some exploration, even despite the deterministic policy, there's noise that is added to continuous actions. And also, for stability, there's exponential recency. So if you recall back from the action value methods, we had different schemes of how we updated values. In this case, we're going to be using the exponential recency mechanism that you'll see on the next slide, so that there's not any big change to either of these parameters, phi or theta. With these key mechanisms mentioned, let's now read through the pseudocode for this algorithm. So let's just start from the top. You can see that the algorithm, it has some initial policy parameters theta and some action value parameters phi, and it has an empty replay memory at the start, which we say is D. We have these parameters that we're initializing with the current values, just so that we can get everything ready for the actual logic of the algorithm. Over here on line 4, what you can see is that we repeatedly observe some states and create we figure out which action we're going to take. Now, mainly the main part of this is just the deterministic policy. So you can see mu parameterized by theta, but we also add in some noise. So some noise epsilon drawn from a normal distribution. We add that onto the action. Finally, we clip this noise. So what we say is this action, if it's lower than the lowest possible bound for the action, we only return this A low. If it's higher than the highest possible action, then we only return that A high. So this is just making sure that the action is in a valid range for the context that we're working with. So this is a deterministic policy with some exploration baked in due to the noise being added. Next, we execute the action, get the next state, reward, and also a done signal. So the done signal D, it's set to 1 if the next state is a terminal state, that is, the episode is ending. We'll use this convention a lot. Now that we've observed the current experience, we store it into the replay buffer, and if we have hit a terminal state, then we reset everything so that we're ready for the next round of steps 4 through 8. Now, for the remainder of the algorithm, we do a learning for the policies and the action values. So we update those parameters by using whatever is stored in the replay buffer. So let's say every n updates, and for n iterations every time, we will run a series of steps in order to get better parameter values. So first, we randomly sample a batch of transitions from the replay buffer, So we take, let's say, B such transitions, and that will constitute a batch of experience. Then we use the TD one-step target that we're used to. The one step in this case, it just indicates the one that we're used to. We'll see another variant in the future that isn't one step. The only thing that might look confusing here is this 1 minus d term, which wasn't mentioned in the past. The only thing that this does is, if we have d equals 1, which means we have hit a terminal state, well, we don't expect any reward after that. So we just keep the reward R, and we do not estimate any reward, any discounted reward being added on afterwards. But if D is 0, like most of the time, this term just disappears and we're left with our normal TD estimated update. I should say TD bootstrapped updates. Then what we do is we minimize the mean square error between the target from TD and the current parameterized action value function, and then we average this across all of the experiences that we had in our batch, and then we can use this to update the policy with gradient descent. So, sorry, I should say use this to update the value function with gradient descent. For the policy, we actually use gradient ascent because what we're trying to do is maximize the expected return. Again, we average this across all samples in the batch. This, this notation of having the absolute value sign and then B, it just means the number of samples that we have in the current batch. So we're just averaging over when we sum and then divide by that number. Finally, when we do the gradient descent and ascent updates, we'll get updated values for phi and theta. We don't directly use them. We have this exponential averaging where you have this parameter polyac, that's what it's called. It is set to something like 0.99, so that mainly these values that we take away for the next round are whatever we currently have, so 0.99, so 99% what we currently have, and then this is like 0.01, so a little bit of the new stuff. So this is like the exponential averaging, which makes sure that the parameter updates are stable. So that's an overview of the DDPG algorithm. As you can see, it reuses many of the same components that we've seen before, just in a clever way to improve performance. When it comes to the results of this algorithm, it was evaluated in a bunch of robotics tasks, and in general, when we used the algorithm, it usually did better than the prior control, so the prior best in these robotics tasks. The thing to note is they compared the algorithm in a low dimensional or high dimensional setting. Low dimensional means that there were just a few inputs, a few scalar values as part of the states of the algorithm. So for instance, there could be hand engineered inputs like, let's say when we're balancing a cart with a pole on it, you know, what is the velocity, what is the angle, etc., etc. The high dimensional bar is when the algorithm just received the raw frames, like in DQN. It just looked at the task visually and had to figure out from the pixels what to do. So usually the results were better when we had the precise low engineered input to represent what current state there is in the problem. But still, even when high dimensional information was fed to the algorithm, and a good number of the robotics tasks, DDPG, still had appropriate performance. To summarize, you can pause the video and check these questions. All right, let's take them up. So why can DDPG work for continuous actions while DQN can't? Because DQN has that epsilon greedy policy with an argmax term, whereas DDPG has a parameterized or approximated policy. Why can't DDPG handle discrete actions? This is a little bit more subtle because we are adding noise to the policy like this? Well, first thing, this won't work if we don't have continuous actions, because we can't just say, add 0.23 to some action and then it will still necessarily be a valid action. Furthermore, the derivative computations involved in the gradient descent and ascent algorithms, they're not going to work well if we have the actions be discrete, because we're going to have to bin the actions, which is a non-differentiable operation. Next up, how do the actor and critic interact in actor-critic methods? We're going to see these types of methods again and again, where we have a separate focus on learning the policy with the actor and learning the values with the critic. Well, as you can see here, when we are updating the parameters phi, this involves us having some actions chosen, and the actions are chosen based on the parameterized policies. Whereas when we're updating the parameter data, that depends on our current approximations of the action values that are dependent on the parameter phi. So both of these actor and critic agents, they kind of interact with each other, where one updates and changes the target that the other is updating towards, and so on and so on. Why can DDPG explore if it has a deterministic policy? Again, the added noise. And why is DDPG limited to off-policy methods? As we talked about with DQN, when we have an when we have a replay buffer, this means that whenever we're doing these parameter updates, we are sampling actions that are chosen by prior versions of the policy, which is effectively like having multiple policies instead of a single consistent policy used throughout the algorithm. Because of this, it's like we're using multiple policies to choose actions when we're updating. The replay buffer, or the experience replay mechanism, limits DDPG to off-policy methods. With that out of the way, take a pause, and then we'll continue with our next modern RL algorithm. Next up, we're going to be talking about one of my personal favorite algorithms. We have the Advantage Actor Critic, or A2C algorithm. This algorithm basically tries to unify the worlds of DQN and DDPG that we learned about. With DQN, we were able to support discrete actions. With DDPG, we were able to support continuous actions. A2C is an actor-critic method that supports both. When we say actor-critic, again, there is one part of the algorithm that is trying to figure out the best policy, another part that is trying to figure out the best critic. One of the main benefits that A2C offers is that it can stabilize learning without the use of experience replay, which we've seen in both DQN and DDPG. Now note that experience replay is good when it's able to decorrelate the samples that we're experiencing, so they're not all from the exact same moment in time, causing us to learn a locally optimum policy. But that comes at the expense of using a lot of memory, since we have to store a bunch of prior experience samples in our replay buffer, and restricting us to off-policy algorithms, because the experienced samples that we're pulling in were generated with old parameters, aka old versions of the policy. So it's not possible to have a single consistent policy that is being used throughout in an on-policy context. Here's an example of the kind of thing that A2C can do. So it can control these, for example, robotic-like figures in simulation. To get into the details of the innovations in A2C, I'm going to use this time to introduce some background concepts and then introduce the main innovation that makes A2C unique. Let's go through this one at a time. So throughout the past algorithms, we've gotten used to this TD target or TD estimate of the overall return, which we call a one-step TD return. In this, we bootstrap, aka use this current estimate of the value function after a single step. So we obtain one real reward. When I say real, I mean actually obtained from the environment. And then this VST plus one term, it's supposed to encompass all of the other, RT plus one, RT plus two, RT plus three, and so on and so on. All of the other rewards in this overall return. The benefit of this is that it's fast. We immediately get a reward, and then we can use the current critic's estimate of the value function in order to estimate the overall return, which will help us in our gradient ascent and descent equations. The problem is that this speed, it has a trade-off. We have a high likelihood of having some error, in other words, bias, because this one value function is required to estimate a lot of different rewards at different time steps. So our overall estimation is likely to be further from the actual return. To contrast this, we can introduce what we call an n-step TD return. This, very simply, takes the single R of t term and then adds on to it more and more experienced rewards. We're not relying on the state value approximation for as many of the reward terms. And by the time that we are, n steps down the line, now gamma to the n is a very small number. And so the overall impact of this bootstrap, of this estimation, is lower on the overall return. So we are less likely to have an error. Obviously, there is a trade-off to be had here. If we have n equals 1, then we're very fast in making updates, but we have a lot of error. If we go all the way to n equals infinity, well, we're very, very slow, but no error whatsoever. So we need to find a reasonable middle ground where we can balance the amount of error in our targets, so in our estimates of the return, with the amount of time we have to spend waiting, gathering real experience, real rewards, before we can update our estimates. The next key ingredient, which is again more so background information rather than a key innovation for A2C in particular, we already mentioned the problem of variance when we just use the estimate of the return, g of t, in our gradient ascent equations. Because g of t can vary a lot from episode to episode. It may be that in one episode we get very lucky. Let's say we are, moving that robot as it were, and we're on very flat ground, everything's nice and smooth. But in another episode, we are now on very bumpy ground and we start performing worse. Well, a lot of variables are at play here. That's just one example, but the key idea is that the total return that we're either collecting or estimating, it can vary a lot, which can make learning unstable because it's hard for the RL agent to tell if the policy that it's using is good in general, or we just got lucky or unlucky in the current episode, and that made G of t much higher or much lower than it usually would be. To fix this problem, we basically need to take this absolute value and make it relative. We need to make this be more relative to the average return we expect versus what we actually got, so that we can figure out, is this unusually high or low, or is this more or less what we expect and we don't need to make many drastic changes. To get closer towards this idea of not having an absolute return, just figuring out whether the actions we're taking are better or worse than average, we're going to introduce a general concept called the advantage function. The advantage just tells us how much better the action we took is compared to the average action we can take in a given state. So for instance, if we're using one-step TD estimates, we want to compare the action value to the actual state value to see if this particular action's value is much higher or lower than the average action's value in that state. Then we can plug in our one-step estimate of the action value in order to get a concrete formula that we can compute. Note that the information that we get from this is if our advantage is positive, that tells us the action is better than average. If it's negative, the action is worse than average, which indicates to us whether or not to increase the probability of our policy picking some action. In the policy gradient equation that we're using in gradient ascent, with the old approach, we might get these large returns. They might vary more or less than this. In the new approach, where we're using the advantage function over here instead of the return, we are now able to get more, let's say, normalized values, more normalized advantages, which tell us more cleanly whether or not to increase the probability of taking some action. Now, all of this, the n-step returns and the advantage function, that's more so background info. It's not like this was invented by the A2C algorithm, but it was used in this algorithm. This next part, though, is very much, the specialty of A2C. So the main part of A2C is using parallel training instead of experience replay. The way it works is that there are n agents, so A1 through A4 in this case, that are initialized in individual environments where they experience different states, they take different actions, they observe different rewards. So they're independently exploring the space of possible solutions to the RL problem. Now, when they're doing this, they will figure out on their own, here's the gradient that I think we ought to compute based on the rewards and all that I've experienced. And instead of using that gradient in gradient ascent, directly changing parameters themselves, you're going to take all those gradients and send them to a coordinator that's going to wait for all of these agents that are running in parallel to finish. When all of the gradients arrive here, the coordinator will average out all of those gradients and then use the average to update the global parameters. So here we might have a theta or a phi for the state or policy functions. After this has been updated, the coordinator will then restart all of the agents to again run in parallel. Now I'm going to state that more verbally. So this is saying the same thing. We run those n environments at once for all of the different worker threads. They collect experiences that are independent, unrelated to each other, send those to the coordinator, which averages the gradients across all those experiences. And then the parameters are updated once with the average gradients. Then we restart this process, so all of that starts to occur again. The key benefits here, one, we can use GPUs for training because we're doing all this work in parallel. We have more diverse experiences because all of those independent agents, they are indeed independent, they're running on different states and environments, which can cause us to explore more. And then the last thing, the reason why A2C uses this instead of experience replay, those average gradients, they're more likely to not change the policy towards a local optimum. It's not likely that after we average all of the updates that each of the agents wants, we're likely to just be left with the best update for one agent based on its current, time or place in the environment. It's more likely that after we average everything, then we're going to get something that is more generally useful across all of the environments. And this is the same benefit that Experience Replay would have offered, but with using more memory resources for storing all of the prior transitions, and also forcing the algorithm to be off policy instead of on policy, like with A2C. So here again are all of the new elements that we'll introduce in A2C, with the parallel parameter updates being the key innovation for this particular algorithm. Let's now look at the pseudocode for A2C. So here's what's happening for each of the threads that you saw. So each of those A1 through A4 circles in the earlier diagram. First, we assume that there are some global parameters, so theta and theta v. Theta is the policy parameter, theta v is the value parameter. That is to say, this parameterizes the policy function, this parameterizes the value function. Each of the threads, whenever they run, they will make their own copy of these parameters. So here's what we do. We first reset the gradients at each thread, and then we make sure that all of the threads, they copy over the same global parameters. So this is the global parameter, and the ones with the apostrophe are the local copies for each of the threads. Now we get started generating what I call here an n-step walk. It just means we sample n rewards so that we can use those to construct an estimated return. So each time step, we're going to perform an action according to our stochastic policy right here that is parameterized by the local copy that the thread has. We'll return a reward, go to a new next state, and then, repeat until we have done this n times. Then, when we have gotten our n-step walk, we're going to construct the estimate, which is the TD n-step estimate of the full return. So we add on 0 for the terminal state, or the estimated bootstrapped state value for any non-terminal states, that is the last state in the walk. And then we start doing this kind of backwards formula to compute the equation that we saw earlier, which was the n-step TD target. After we've computed this, for each time step along that n-step walk, what we do is we compute the gradients that we want. So here is the policy parameter gradient, and this is the value function gradient. So here we're computing the gradient with the log of the probabilities. This is the policy gradient part, and here r minus the state value function, that is from the advantage function, in this case the n-step advantage function. Down here we are using the gradients to minimize the mean square error between our n-step estimate of the state value and the actual state value. So now this will be minimized with gradient descent. This will be maximized with gradient ascent. So after we've computed the gradients in each of these threads, we can send these to the coordinator, and that, when it receives everything, receives all of these gradients, it will run the gradient descent and ascent equations. This will result in new values for theta and theta v, the global parameters, and then we go again. The coordinator will restart all of the threads, give them all the new updated parameter values, and we repeat the process until we are, done with the maximum number of iterations. So that's the A2C pseudocode. In terms of results, A2C was quite effective compared to DQN and DDPG. These top graphs here, they show in yellow how A2C performed. Note technically that this code here, it shows A3C results, which is a less optimized older version of A2C. It just did the synchronization steps differently. But in any case, this helps give us an idea. Even this less optimized version, in the discrete tasks, so this is playing the Atari games that we saw in the DQN section, it's consistently outperforming most other methods, including DQN. When it comes to continuous tasks, the authors tried it in a race car driving simulator. In this context, the final A2C algorithm, well, A3C in this case, it did not beat humans, but it did perform best out of some other alternatives, simpler alternatives that they tried out. So in both the discrete and continuous action contexts, A2C was a major step forward. With this being mentioned, that wraps up our A2C section, and we're going to talk about a rather complicated algorithm up next, so take a break and come back when you're ready. Before continuing into TRPO, I noticed I accidentally skipped these checkpoints for A2C. Let's just quickly go through them. First, how does the advantage function reduce variance compared to the row returns? With the row returns, we can have the possibility of returns being very different from episode to episode because of fluke factors, like we, let's say, happen to have a good bit of environment to work with. Let's say we had a robot and it was on smooth ground instead of flat ground, but that doesn't mean that our policy is necessarily better or worse. With advantage functions, we reduce the magnitude of variability like this. We do this because the advantage function, it takes the expected value of the action taken and subtracts away the expected value across all actions possible in any given state. This centers all of the advantages around 0 instead of, let's say, around some high return number, which allows us to reduce changes to the actual policy when we're uncertain that the benefits are significantly different from what we expect in the average case. What are the pros and cons of memory replay versus parallel training in order to reduce local temporal optimization? So when it comes to temporal optimization, again with that robotics example, we don't want a robot that just optimizes to drive on, let's say, currently bumpy ground. We want it to be able to drive in various environments in general. So what we don't want is highly sequential inputs, states, actions, etc., that force the RL agent to learn a policy that just works right now. Parallel training, it fixes this by having N agents in independent environments that are taking different actions in different states, less likely to optimize towards just a single beneficial situation that's happening right now. because we take whatever the updates each one wants to make are and average across them. In contrast, memory replay, it stores transitions experienced over time, and instead of just looking at what's happening right now, it kind of reviews its memory and goes and updates over past experience transitions as well. Now, parallel training, it's good because it can cut down the actual training time by leveraging GPUs and other hardware. Each of those independent parallel agents, it can run in an optimized fashion, more quickly. It can also support on-policy algorithms because there is just a single synchronized policy that each agent is using in the different environments. The problem is that we are dependent on hardware for the parallelization. So if hardware can support 10 agents running in parallel, that's kind of what we're stuck with. Whereas with the memory replay, one benefit is that we can support off-policy algorithms, which is useful in, certain contexts, but also we can store much more transitions in memory and review them compared to the number of parallel agents we can run, because the ability to compute in parallel is a lot more difficult than the ability to store lots of data. RAM is cheap. We can store gigabytes and gigabytes of data. Next, how is A2C different from DDPG? Well, among other things, so A2C is on policy, DDPG is off policy. A2C involves the parallel training, DDPG involves memory replay. Also, DDPG is limited to continuous actions because of its deterministic policy that outputs a specific action value and adds on a continuous, amount of noise, perturbation, disturbation to that particular action. And in contrast, A2C, it doesn't do any of that. It just has a stochastic policy, an approximated stochastic policy that just runs a parameterized function whenever we want to compute the probability of any action, so that it doesn't depend on the number of actions we have. It can support discrete or continuous actions. Next up, we can dive into the details of TRPO. Now, this is an old and complicated algorithm, which is called Trust Region Policy Optimization. It's been replaced by a simplified version of itself, which is called PPO. I'm only including this here so that we can cover the basic building blocks that we need in order to learn about PPO. So TRPO is on policy again. It has a stochastic policy again, just like A2C, so that it can explore. The main improvement that it brings over A2C is that it avoids large policy changes in any one gradient descent step. This enables it to stabilize the learning over time. Now, in order to avoid large policy changes, we need to measure how different the new policy is compared to the old policy. And because both of these policies are stochastic policy distributions, well, we need a mathematical tool to measure the difference between two policy distributions. This tool is called KL divergence. Here is the formula for it. I'm going to give you the intuition for why this formula makes sense. The basic thing that it measures is how surprised we'd be if we sampled some events from one policy distribution P. However, we used policy distribution Q to estimate how likely that event is. Now let's consider three cases for the inside of this sum over here. Let's say P of x is approximately equal to Q of x for some x. That means these two probabilities are roughly the same for that particular event x. In that case, this becomes one number divided by roughly the same number. So we have just 1. P of x multiplied by log of 1. Well, log of 1 is 0. We overall get 0. So for events x where the two policy distributions are similar, then the overall KL divergence is, it doesn't grow, which is what we'd expect as a measure of the distance between two policy distributions. Let's consider the case where P of x is approximately 0 and Q of x is approaching 1. In that case, this simplifies to approximately 0 over approximately 1, which is about 0, right? So this is about 0, this is about 0. We have p log p, where p approaches 0. Now note that log p, it changes a lot more slowly than p. P will change linearly, log p will change logarithmically, a lot more slowly. So what we notice is that overall, this p term tends to dominate, and the overall limit, it goes to 0. What this means is, in this case, where p of x goes to 0, q of x goes to 1, DKL divergence doesn't change much. Why does this make sense? Because we're measuring how surprised we'd be if we sampled an event x from probability distribution p, and then we did whatever. But if we're saying p of x approaches 0, then sampling this event is unlikely to begin with. So this event should not factor much into our KL divergence. Now finally, we have the last case, if p of x approaches 1, but q of x approaches 0. In this case, we have 1 over approximately 0, so we have 1 over q, q approaches 0. This is going to go to infinity. So KL divergence is going to blow up, because we're saying that the original p, it had a high likelihood for this probability, but q says it has a low likelihood. So this is a very flagrant change between the two distributions. We should be very surprised. Finally, all of these inner terms are being summed across all the possible events x that this probability distribution ranges over. Yes, you could have an integral here, continuous case and whatnot, but I think you get the idea of how KL divergence measures the difference between two probability distributions. In TRPO, we apply this in the following way. Let's say, in abstract terms, we're going to update our parameters as follows. We define some advantage function, L of theta old and theta. It compares how much better the particular alternative parameter theta is relative to the old parameter theta old. And then we, run this across all the possible thetas and choose the best theta out of all those. So with TRPO, the thing that we do is we constrain this parameter update strategy with KL divergence. So we only go forward with actually updating the parameter if the KL divergence between the old and new parameterized policies is less than some threshold delta. So here you see we are taking the KL divergence of the old and the new policy, which is, the expected value across all the actions. And for P and Q, I just subbed in the old and the new parameterized policies. And then we make sure that, this is an expectation over action, this is an expectation over states. So we make sure that across all states, that the KL divergence is less than some threshold delta if we are to accept this particular update. So this enforces a trusted region meaning in this particular region, the policy is not updated too much. We're not going to have instability. You can go forward with the updates. If we do not satisfy this constraint, we do not go forward with this update. Now, in terms of the advantage function, right? So we had L of theta and theta old. Ideally, we wouldn't need the theta old. We just ideally measure the advantage function as we had before. So take the action values and then subtract away the state values, which are the average action value in that particular state. Ideally, we'd do that. The problem is that we cannot estimate the action and the state values for every single parameter theta that we want to take the argmax over. So we can't compute this for every data because every time we want to compute it, we're going to have a different policy because of the different parameter data. And that's going to influence our estimates. So this is going to be computationally infinite. It's not going to be possible. To solve this, we need to introduce another mathematical complication. So this is, I warned you, TRPO is complicated. We need to introduce something called importance sampling. This is where we use the the action and state values for the old parameter instead of trying to figure out for every parameter theta what these values ought to be. I'm going to prove importance sampling for any function f of s and a in this case, and then we'll apply it on the next slide to TRPO in particular. So let's say we have this expectation that we're computing. So we're computing the expected value of this function over all possible states and action pairs generated by the policy that we currently have. If we break this down using the definition of expectation, you can see these sums and also the probability that is generated by the policy distribution multiplied by the actual value inside the expectation. I just multiplied, both sides, multiplied in a constant of 1 here, and 1 that is the same as the exact same number divided by itself. The number I chose in this case is the probability of choosing that action under the old policy distribution. Now, I took this numerator, kept it here, but I moved the denominator over here. And note that this part over here, the sums and this policy probability, it reflects the same structure as we had over here. So what we can do is actually take all of this stuff in square brackets and make this like, f prime of s. So just a adjusted function, whereas this stuff, it is absorbed into an expectation. So as you see here, what we've done is we took an expected value over the new parameter theta, and we rewrote it in terms of the expected value over an old parameter theta old. The only change we had to do was define this probability ratio, which says, hey, if you're going to use this fs of a, as it was before, you need to adjust it. You need to weight whatever that function value returned with the amount that the probability has changed, aka the probability ratio. So this is what importance sampling does. It allows us to replace an expected value over one probability distribution and rewrite it in terms of another probability distribution. Applying this to importance sampling, so we ideally wanted to measure this function, but we did not know, what the action and state values were for each and every theta. We only know it for theta old. So why don't we rewrite our expected value using importance sampling? If we define f of sa as this particular function, then with importance sampling, we can replace this expected value with the 1 over the old policy distribution, introduce in the probability ratio that we see here, and then these terms, so the state and value functions, are the ones generated under the old probability distribution, aka the old parameter values. So we don't need to change this term for each and every policy that we want to consider. So in summary, here are the equations that we need for TRPO. This is the advantage function that tells us if a particular theta value So a particular parameter is better than the old parameter. We have subcomponents here, which are the probability ratio and the advantage function as defined here. And we have this particular KL divergence equation. And we use it to say that TRPO, it solves this problem. We maximize the new parameter value such that the KL divergence constraint is not violated, aka the parameters don't change too much all at once. This is possible in theory, after a lot of theory, I'm sure you'll agree. But the second part of this, the KL divergence constraints, it creates lots of complications in terms of the optimization algorithms we can use. We can no longer just use plain old gradient descent or ascent if we do an optimization like this. So those are the key building blocks on this page. All of this is the key information that we need to take away from TRPO so we can learn about its successor, PPO, which will simplify and solve this problem. Just before we wrap up, check your understanding of what we learned about. Let's take up these questions. So what does KL divergence measure in the context of policies? It measures how much a policy has changed after we updated a parameter. And second, what's the main idea behind importance sampling? It's so that we can rewrite an expected value over one policy in terms of an expected value of another policy. This allows us to use, let's say, certain information we have available from the old policy, like the state and action values, and reuse those when evaluating new policies where we don't have time to estimate that data once again. With all that out of the way, congratulations, you made it through the complexities of TRPO. Next up, we're going to learn how PPO helps us simplify this situation into a practical and reliable algorithm. PPO is a very impressive modern RL algorithm that's kind of the default for most industrial applications. It stands for Proximal Policy Optimization, and it has been used in many impressive contexts, including playing complicated video games like Dota 2. The main idea with PPO is to achieve the same thing that TRPO does, just simpler. It's still trying to limit updates to parameters to be in a certain trusted region where the updates are not too large to make the learning unstable. But it achieves this by modifying the objective function that normal gradient descent is maximizing instead of adding a separate and complicated KL divergence constraint that prevents us from using gradient descent. Let's now look into the details of how it modifies the objective function to do this. With PPO, we will take inspiration from the old objective that we learned about. So the TRPO objective, which was just the expected value of RT80. RT is the probability ratio, which tells us how much the new probabilities under the new policy are different from the old probabilities under the old policy. AT is just the advantage function. It tells us if the actions we're taking are better than the average actions in a state or worse than the average actions in a state. Note that if the probability ratio RT is much lower than 1 or much greater than 1, that tells us that the policy has changed a lot. The probabilities have changed a lot, and that's not so good for stability. So the goal of the modified TRPO objective, aka this clipped objective that PPO will use, it's going to be to keep RT around 1 to make sure the probability ratio does not change too much in any one step. The way that we do this within PPO is to use what we call a clipped surrogate objective, which has this very ugly formula here, which we will explain on the next slide. Though I do want you to note that there is this parameter epsilon. We use it to define how far from 1 we are comfortable with when it comes to the probability ratio RT. So RT within the PPO context is going to stay within the bounds 1 minus epsilon and 1 plus epsilon. So let's say epsilon equals 0.2. It's going to stay within 0.8 and 1.2, so pretty close to 1. Now let's explain how this ugly formula achieves that result. We're going to do so mainly visually. So I've copied over the exact same equation from last slide onto this page, and I've graphed it for various probability ratios. I've graphed the old equation with this blue dotted line, so that's from TRPO, and I've graphed the new equations within these red lines, which is from the clipping function you see here for PPO. This vertical black line, that is RT equals 1, and the dotted orange lines around that give us the trust region, or the region of acceptable updates. So we're fine with the probability ratio being within this region for any given update. Now let's look at this ugly function. The first component within it is this clipping component. So the clip function, it takes an RT and the lower and upper bound, 1 minus epsilon and 1 plus epsilon. If RT is within these bounds, no problem. The clipping function just returns RT. But if it is lower than 1 minus epsilon, we just get back 1 minus epsilon. If it's higher than 1 plus epsilon, we just get back 1 plus epsilon. So the clipping function, it constrains RT to be within these bounds. The min function is, as you'd expect, it returns the minimum of the two numbers that we have. So now let's look at what this clipping function is doing. We'll start with this first case where we have a positive advantage on the left. If we have a positive advantage, that tells us that the actions we're taking under the new policy, they are on average better than the actions we could take in the state that we're in. So we want to increase the probability of these actions, just not too far. We don't want to go beyond 1 plus epsilon, in this case 1.2. So look at what the clipping function does here. It basically is the same as the old TRPO function in most cases, but if the probability ratio is getting too high, well, the objective is clipped off. It doesn't keep increasing anymore. And that means that we can't continue to just optimize the parameters to get higher and higher RT. Yes, we do want the probability to be increased under the new policy for this good action, but not too far. We don't want it to go beyond 1 plus epsilon, which would cause instability, which is why we see this clipping behavior in just this one context. To explain why this clipping behavior occurs, we can just look at the math formula. So we have an RT in this region over here. RT is greater than 1 plus epsilon, this upper bound. So the clipping function is going to take RT, see that it's higher than the upper bound 1 plus epsilon, and just return 1 plus epsilon. Then we have the minimum of RT80 and 1 plus epsilon 80. As we just said, RT is higher than 1 plus epsilon. This means that 1 plus epsilon 80, that is the smallest term. So that's what the minimum will return. And that is why we can see that RT continues to increase, but with the clipped function, we're always getting back 1 plus epsilon 80, and the clipped function is no longer increasing. In the other cases, well, we can do the same case-by-case analysis. So let's say RT is within these bounds, within the upper and lower bound. The clipping function is just going to return RT, and the minimum of RT80 and RT80 is just RT80. They're the exact same, which is why the old TRPO function in blue and the new objective function in red, they're the same. In this last case, where RT is less than 1 minus epsilon, the clipping function, it returns 1 minus epsilon, and then you compare RT80, 1 minus epsilon 80. As we said in this region, RT is less than 1 minus epsilon. So the minimum of the two is going to be RT80, which is why these two are the same. Within the negative advantage case, so we have an action that is chosen that's, worse than the average action possible in a state, we see the opposite behavior. So because the action is worse than average, we want to decrease the probability of it occurring, but not too far. We don't want to decrease the probability ratio lower than 1 minus epsilon, which is where we see this clipping come in. Again, we can analyze why the clipping occurs by looking at this formula. It's just a little bit more messy because 80 is now a negative number. So let's say we have an RT value in this context, so RT is less than 1 minus epsilon. The clipping term, it returns 1 minus epsilon AT. And then we have RT80, 1 minus epsilon AT. We have to figure out what is the minimum of those two. Note that RT80 is a small negative number because AT is negative, and RT has a lower magnitude than 1 minus epsilon. Whereas 1 minus epsilon AT, it is a large negative number because AT is negative and RT is less than 1 minus epsilon in magnitude. So if we take the minimum of a small negative number and a large negative number, well, the large negative number is the minimum. So that's why we get back 1 minus epsilon AT, and that's why we see this clipping behavior. You can continue the reasoning in these other two cases, but the key idea is that when we're likely to over-optimize, so we want to increase the probability, but we're increasing too far, we're taking RT beyond 1 plus epsilon, or we want to decrease the probability ratio, we want to make an action less likely, but we're going too far, we're taking the probability ratio RT lower than 1 minus epsilon, then we see the clipping behavior come in. Otherwise, the PPO function is just the same as the old TRPO function. Now, what's the point of this clipping behavior? Why is it helpful within gradient descent to stop it from going too far? Well, keep in mind here, so this is 1 plus epsilon AT, and this is 1 minus epsilon AT that we're getting from the clipping function. If we introduce the gradient descent equations, you'll see here's the gradient descent equation. We're going to end up with one of these three things, RT80, 1 minus epsilon AT, or 1 plus epsilon AT, depending on which part of the graph we're looking at. Note that when we bring the gradient inside, so we actually compute that gradient, taking the gradient or derivative of RT, a function of theta, that's fine. But if we take the derivative with respect to these constants, 1 minus epsilon or 1 plus epsilon, we just get back 0. So when we're in this region of over-optimization, where we have 1 plus epsilon AT or 1 minus epsilon AT, well, this derivative is going to be 0, and overall this term becomes 0. So we're left with theta new is equal to theta old, i.e., when we're clipping, because we're liable to over-optimize, the PPO function is defined in such a way as to stop that behavior. It stops the parameters from updating. It stops the over-optimization. That's the key insight of why this clipping function is the way it is. It is a simple way to prevent over-optimization. We literally, put emergency brakes in. If we're going too far, then we're going to stop the gradients from having a value. They're just going to be 0, and the parameters are going to stop changing. And keep in mind, this is all very computationally simple. We don't have a complicated KL divergence equation that is separate from this gradient descent algorithm. We're all doing it with simple clipping operations and min operations that we're able to reason about even in our head. With that defined, so that is the key idea behind PPO, is that clipped objective, but there are a few other features that are useful. First, we have heightened sample efficiency due to that clipped objective. By sample efficiency, I just mean that whenever we have a real-life interaction, we get a sample of state, action, reward, and so on. We can do multiple gradient descent steps on it because if we're liable to go too far, well, as we just saw, the clipping function will allow us to automatically hit the brakes, make the gradient 0, so that we prevent further parameter updates and prevent over-optimization. This creates some data reuse because we can perform multiple updates on that same, that same time step, but we still have less data reuse than memory replay, which could theoretically keep drawing the same experience again and again from its memory buffer and replaying it. Next, I should note that PPO is unlike reinforce in that it is an actor-critic architecture. Just like DDPG and TRPO, it has a parameterized policy and value function being separate, and this makes it more stable. It's not trying to do everything all at once. Finally, there is one last new thing to note about PPO. It has what we call this fancy word right here, entropy regularization, which is just a big word to say that we reward exploration. We give the PPO algorithm a bonus when it has a more stochastic policy, a policy that is more likely to choose more actions instead of just selecting one action all of the time, a near deterministic policy. I'll just quickly expand on this because we haven't seen this building block within RL algorithms before. So visually, here is the definition of entropy. If we compute this entropy function of a probability distribution, in this case a policy distribution, when we have a near uniform distribution, so the probability is all spread out, you're very likely to not repeat the same action selection multiple times. In that case, we have high entropy. You can see this value right here, it's 2.3. When we have a distribution that is getting more and more deterministic, one action is being chosen more and more of the time, then we have a lower entropy. So this function takes in that policy distribution and returns 1.1. Now let me define the math formula for this function. Here it is. So you pass in a probability distribution, in this case our policy distribution, and then you compute this formula. Now, I can't fully prove to you why this formula makes sense, but I will prove to you this part. I will show you that if you have a near deterministic distribution, the entropy is actually minimized. I'll just leave it to you to figure out why, if you want, the entropy is maximized when we get more and more stochastic distributions. So in that one case, if the policy is becoming more deterministic, we have one action, A prime, whose probability p prime is approaching 1, whereas all of the other actions have a probability approaching 0. So then this sum, we can break it apart into the one action A prime and all the other actions A. So for the one action A prime, we have probability p prime approaching 1, and we have the probability times the log of the probability, so p log p. For all the other actions that are A, they're not equal to that one A prime action. Then we have the probabilities approaching 0, and we again have the limit of p log p. In this case, as p prime approaches 1, we get 1 times log of 1, and log of 1 is 0, so this overall limit is equal to 0. In this case over here, well, we have a linear factor here, p, and a logarithmic factor, log of p. A logarithm changes more slowly than just the linear term. So p, as it approaches 0, that is changing more quickly than the logarithm, which is why the overall limit, it tends to 0. Overall, we have minus 0 minus a bunch more zeros. So we have shown that the policy, as it becomes more deterministic, has 0 entropy. So overall, what we can do is, if you trust me on the latter half, the part that I haven't shown, that as you have less determinism, the entropy rises, well, we can just add the entropy into our objective function that we want to maximize with gradient descent. We just add on C times the entropy of the new policy, where C is any constants, and we can increase this constant if we want to prioritize having a more stochastic distribution, or decrease it if we care about better focusing on the clipping loss. That now defines all of the components of the PPO algorithm, so we can now look at some pseudocode. So you can see here from the actor critic part, we have policy parameters theta naught and value function parameters that are separate, phi naught. These are used for estimating state values. For however many iterations we want, we're going to generate a set of trajectories. So we just run the policy, choose actions again and again based on our current parameters, theta k, and we will store all of the rewards that we're getting as we choose these actions. Then we use those to compute the n-step bootstrapped TD return that we have seen earlier, where we just add the discounted sum of all the rewards, and then at the end, all of the remaining reward time steps that we haven't seen, we just approximate those with the bootstrapped value function based on the current value parameters phi. We use that return to then compute the advantage. So what is the return that we got given the actions we chose, minus the average return that you'd expect if you were to start with state st and then take whatever average actions you wanted. So that gives us our advantage function. And now we have all the ingredients we need to start updating the policy and the value functions. So for the policy score, we compute the function that we just defined, where we're averaging, taking the expectation across all of the trajectories that we generated. For each one, we're computing this PPO clipping loss, and then we add on the entropy bonus. And we've defined all the equations that we've seen so far here. And then we simply apply gradient descent to maximize this objective function. So we change the parameters such that this function is maximized, keeping in mind that the clipping function will prevent us from going too far. Finally, for the value function itself, we have again an actor critic architecture. So the critic part, it is trying to minimize the mean square error of the actual bootstrapped value function and our estimate of that, which we're using the bootstrapped n-step TD rewards as the target here. So we take the error here, square it to get the square error, and then average or take the mean across all trajectories and all time steps within each episode. So that is our loss function, and we minimize it with gradient descent. And that's all there is to it. That's the PPO algorithm. In terms of results, you can see here how PPO is performing in some continuous robotics tasks. Although PPO is quite versatile, it can be used in multiple contexts, including discrete tasks, because of its stochastic policy. Anyways, you can see this purple line PPO. It's performing better than a number of other algorithms, usually better than TRPO, because of the more improved stability and reduced complexity that we have here. It's also being compared to some other algorithms that we've seen, like A2C and a reinforced-like algorithm. Just before we wrap up this section, quickly stop the presentation and try and answer these questions, and then we'll take them up. Okay, so first off, what's the benefit of the clipped objective in PPO? Well, because of that clipped objective, we are able to have, let's say, an automatic braking system. If we're moving the probability ratio too far outside the bounds, we're going to have the clipping function come in, and it's going to introduce a 1 plus epsilon at or 1 minus epsilon at temp. If we take the gradient of that is 0, and so the gradient update stop. How does PPO encourage exploration? We have the entropy regularization. So we give an entropy bonus, which is maximized when we have a more stochastic policy. Finally, why can PPO reuse data for multiple epochs? So, run gradient ascent or gradient descent on the same data multiple times, whereas policy gradient methods usually cannot. Well, again, the clipped objective, it will prevent us from going too far. If we're maximizing or minimizing the probability ratio too far beyond the bounds, the clipping comes in and stops us from going further. With that being said, that is PPO, and we will next have our last modern RL algorithm for this entire video. Come back when you're ready and we'll wrap this thing up. SAC stands for Soft Actor Critic, and these days it's this RL algorithm which is very commonly used in robotics. It specializes in doing continuous actions only for these robotics types of tasks, and the main innovation that it tries to achieve is being very robust. Robust being that it can handle a variety of changing situations instead of just being stuck in one way of approaching the environment. For instance, you can see this robot here. It's learning to walk on a flat surface, but also stairs, also running into some Lego bricks, also on changing slopes, and so on and so on. So let's dive into the details of how it can do this. Most RL algorithms, especially when we look at this continuous robotics domain, they tend to be brittle. That is to say, they're not robust. When we run them in a simulated training environment, they'll do great. They'll walk on the perfectly flat floor, all fine. But when the environment changes, they get new states that they haven't been exposed to. Now they start failing with just tiny changes, like let's say the ground now becomes slightly bumpy. So this means that they're overfitting to specific conditions. And to overcome that, well, we need to show them lots of different conditions. We need to give them lots of data and lots of real world experience, which is very sample inefficient. What we'd like to do is figure out how we can make policies that are robust while at the same time being sample efficient. They're not just relying on seeing every possible situation and memorizing it. The way that SAC does this is with a few key innovations. The first is entropy regularization. As we've seen with PPO, we give a bonus to maximize that encourages stochastic policies, ones that explore lots of different actions. Next, we have off-policy learning, where we use experience replay. That addresses the sample efficiency problem, where we're not just relying on experiencing lots of different conditions. Every condition that we have, we save into the replay buffer, and then we can review that later so that we can be more sample efficient. Next, we have a stochastic policy for obvious reasons. We want stochasticity. We do not want a deterministic algorithm that always picks one specific action. And this also allows us to work with continuous actions, because if we're just outputting probability distributions, it doesn't matter how many actions there are. The last key building block within SAC is new. We haven't seen this before. It's called double Q learning. The way that this works, or the goal that it tries to achieve, is basically trying to prevent an overestimation bias that's very common, where often RL algorithms, they will overestimate how good specific actions are. So to look into the details here, here's how the overestimation usually happens. We usually have a critic that is minimizing the mean square error between the approximated value function and the actual target. And the target could be something like a one-step TD, bootstrapped estimates, as you see here. The problem is that this estimate involves this max term, where we choose the action that gives us the highest Q value. And this causes overestimation, because our policy is not going to choose the max term. It's going to be stochastic, it's going to explore. So if we assume that, we take this particular action, which gives us the best action value, and that's the target that we're trying to optimize towards, well, our approximated value functions are going to go way too high. They're going to get overestimated. So they'll assume that certain actions are better than they actually are. To fix this, we have a minor adjustment. So we still have the same policy that we're used to stochastically, but we also train two different critics. So Q1 and Q2, two separate value functions with two separate parameters. And when we're computing the actual mean square error here, we don't have a max term anymore. We use the smaller of these two Q functions. Note that while this equation is nice and tidy, we do need to complicate it with the entropy regularization that SAC uses. So here you see on the left half of this equation, the entropy regularization equation that you saw earlier in the PPO section. The only one change that I'll introduce here is we have this policy. We're summing over all the actions, so this probability over all the actions. This looks like an expected value, so I rewrite it as such, bringing the negative sign and the log inside the expected value. Why do I do this? Well, over here, I am now able to take this stuff inside the expected value and add it to my target. And this stuff outside the expected value, the sum across the probabilities, that will get baked in to our objective to, minimize right here. So this is just a more concise way of writing this entropy regularization. Now let's go into the policy. So we've looked at the value functions. Let's now look at the stochastic policy. We'd like it to maximize the expected value of the actions that we are choosing. So we want it to maximize this expected value. The only thing is that we also want to add entropy regularization. So just like before, we will add in this little term right here, and we will take the expected value over all of the possible actions. So this will encourage us to explore, not just maximize the expected value of the actions we choose. The only problem here, we have seen this before, we are sampling actions with respect to this policy pi, but that is actually dependent on data. So when we want to compute the gradient j of data, well, we're sampling with respect to something dependent on data, and the value itself is dependent on data. We're in for a little bit of a mess here. Earlier, what we did was we introduced a importance sampling method so that we could use this technique within TRPO and PPO to compute gradients feasibly. Now what we're going to do is slightly different. We're going to introduce a reparameterization trick. What we do is we train our actor, so the thing that's learning the policy, to output the mean and standard deviation of the policy distribution, instead of outputting every action probability. Then we sample some noise from a normal distribution and note that, the noise doesn't depend on the parameter data. And finally, we scale the noise by using these fixed mean and standard deviations, which, were outputted by the actor. So we take the noise, multiply it by the standard deviation, and then add on the mean. Now we have the normal distribution actually centered around the policy distribution. The main aim here of this reparameterization trick is that now we have this, continuous action that we're supposedly choosing, but it is dependent on what we sample from this normal distribution. We're not sampling anything from the policy distribution. We just take the mean and the standard deviation of this distribution. So now we can modify our policy gradients that we're choosing, so the thing that we're trying to maximize. This was the old equation. Now, wherever I see the action A that was sampled from the policy distribution, instead I'm going to use this function here, which has a epsilon value that is sampled from a normal distribution, independent of data. With that out of the way, we can look at the SAC pseudocode. And this is the longest pseudocode for this presentation, but hey, it's the last one. So we have our initial policy and our two phi parameters. So these are two action values because of the double Q learning. We also have an empty replay buffer. We are using this polyac averaging that we saw earlier. So we're gonna, use some exponential averaging here for the actual phi functions so that, there is stable learning. We're not changing these parameters too quickly later on. But at the start, we just, initialize the exponential averaging to whatever our initial values are. Over here, you can see that we're, observing some state, selecting some action with our actual policy. We execute the action, observe the next state, the reward, and the done signal that we've seen in past algorithms, and then we store it into the replay buffer. If we have reached a terminal state, we will go back to step 4 and, restart an episode. If not, then we run a few updates. So let's say every 5 steps, every 5 things we add to the buffer, we will do an update. And we will do, let's say, m updates at a time. Each time, we're going to sample a random batch of transitions from the replay buffer and compute our targets, where this is the exact same function that you saw earlier, except we have this 1 minus d thing, which is, we have d equals 1 when we're in a terminal state. So we have 1 minus 1, this becomes 0, and we have no, reward after the current time step because it's a terminal state. Everything is over. There's nothing after that. Over here, you can see the target is using the minimum of the two values, and that is because of the double Q learning. We also have this notation, A with a tilde on it. That is the reparameterization trick that we talked about earlier. So now that we've computed the target, we can update the Q functions. So we update each of these value functions with the mean square error being minimized with gradient descent. And we also update the policy. So now we're maximizing J of theta using gradient ascent. And this is the equation that you saw earlier as well. Finally, the polyac averaging that I mentioned. So you set polyac equal to, let's say, 0.99. So each new value is basically the old value plus a little bit of what you want the update to be, which makes for stable parameter updates. And you keep doing this until you converge. Hopefully at this point you can see a lot of similar elements to past algorithms we've seen, and you see what I mean about many RL algorithms having similar building blocks that get reused in new and interesting ways. When it comes to the results of SAC, we can see it being compared on some continuous action tasks, because this thing can only do continuous tasks. It's compared to DDPG, PPO, and this other algorithm called TD3, which I didn't cover in this presentation, but it's comparable to SAC, similar idea, similar aim. What you see is usually you'll see a more stable curve for SAC because of what we mentioned. We want it to be robust, brittle, change slowly, be stable. Sometimes it is overperforming most other algorithms, and especially in the most difficult tasks, say this humanoid robot control task, it is significantly overperforming compared to most other algorithms due to its exceptional stability. So to summarize, why do you want to use SAC as opposed to PPO, which is the industry standard? You'll want to use it in continuous action spaces when sample efficiency is very important. So for example, real robots where, it takes a lot of time for the robot to interact with the real world. It's going to be slow, it's going to be clunky. It can't just, take a bunch of GPUs and run lots of simulations. That's not gonna work. Well, you're gonna need something like SAC, which is more sample efficient than PPO. Also, when you want robustness, so your environment's likely to change, or you want off-policy learning instead of on-policy learning like in PPO. When you don't want to use it and you want to use PPO instead is when you have discrete actions, because this only supports continuous actions, and when rewards are very sparse, which means you only get a reward after lots and lots of time. There are lots of time steps where you don't get any reward. Then SAC doesn't tend to perform well. And overall, just take away robotics. SAC is very useful in robotics. Let's just quickly check our understanding. So pause the video and then we'll take this up. First, why is double Q learning used? We use it in order to prevent an overestimation bias that often exists within most reinforcement learning algorithms. How does encouraging high entropy improve the robustness? Well, it makes the policy not rely on just choosing any one strategy or any one action most of the time. And it also introduces more exploration, which is useful. Finally, what is the reparameterization trick? Well, we don't want to sample actions from our actual policy because that will complicate the gradients computation. So we just sample from a fixed normal distribution, then multiply by the standard deviation of our policy, add on the mean, and now we have a new normal distribution centered around our policy distribution. However, we're not sampling directly from the policy distribution. This will simplify our mean. With all of that being said, we can finally just conclude. I'll just do this right now. So in comparison, for all of the algorithms, here's a quick table that I produced. We have early algorithms like DQN, which are still using simplistic policies, and we gradually evolved with stochastic policy. That's, where most algorithms are these days. DQN was only discrete. We introduced DDPG to support continuous domains, and then we now have a bunch of algorithms that can do both, except for SAC, which it specializes in robotics. In terms of sample efficiency, SAC is best, and the others, usually they're using memory replay. Sometimes they have agents in parallel, or they iterate on the same data points again and again to add a little bit more modest sample efficiency. And in terms of stability, we introduced various mechanisms like polyic averaging, or averaging across agents, having trust regions, different ways to try and prevent very large updates over time. Here are some common use cases that you'll see these RL algorithms in. Finally, to return to my zoology analogy, so, a zoologist just sees the different building blocks of the animals. We now see the different building blocks that tend to get reused across lots of different RL algorithms, and we can figure out what are the trade-offs that are introduced with each building block. So the first building block is our bootstrapped estimates. We've been using these TD estimates, like let's say one-step versus n-step estimates. We trade off accuracy when we go towards one-step estimates, but we get more speed. We can make an update every single reward that we get. But with n-step estimates, now we have to collect more data before we can make the updates. This is more accurate, you have less bias, but you will be slower for updates. When it comes to the parameterized value and policy functions, the parameterization can influence whether we support continuous or discrete actions. Often when we're doing stochastic policies, then we can have support for both types of actions. And note that these parameterized functions, well, they're in general, better than the non-parameterized or tabular equivalents. So those tabular methods that we learned about early, they take up lots of memory, you store individual, values for each action. They don't scale to large action or state spaces. When it comes to actor-critic methods versus policy gradient methods, the actor-critic ones, they separate the part that learns about the ideal policy and the part that learns about the ideal values, whereas policy gradient methods just optimize the policy directly. So the trade-off here is having more stability when we have the actor-critic methods versus having more simplicity, which is doing less, computing less, and so on with policy gradient methods, but things tend to be harder to pull off, things tend to be more unstable. When it comes to on-policy versus off-policy learning, oftentimes we are trading off some simplicity. On-policy is usually simpler, but also we have some trade-offs for sample efficiency and stability. With on-policy learning, we have a single policy that is being updated. Often there are more mechanisms to make that stable compared to off-policy, where we have potentially lots of different policy versions in play at once. Usually, this comes up in the context of memory replay. When we use memory replay, the past experiences that we draw from, they were generated by old versions of policies, so you don't have one consistent policy. The benefit of this is that you can have better sample efficiency with this off-policy learning. We also learned about entropy regularization as a building block, key idea being how you balance the exploration and exploitation trade-off. And note that, having more exploration, it can improve robustness so that you're not just going all in on trying to choose one type of action. We looked at trust regions. This was in TRPO and PPO, and how they can be, they can be used to control the stability of the algorithm, prevent excessively large changes in any one time step. But if you implement them in the wrong way, like in TRPO, it's not the wrong way, but it's a more complicated way, you might end up with an algorithm that is much more complicated to, let's say, fine-tune and use. Finally, we looked at experience replay and parallel training. When I say versus, these days, they're usually used, both of them. But in the algorithms we looked at, we had these two mechanisms to balance sample efficiency. And parallel training, it also had the accidental benefit or the side effect of improving our memory consumption and speed usage because we're not storing a full replay buffer and we're not just training in one environment at a time. So this was introduced in A2C, as you'll recall. Overall, if you want to look beyond our zoo and look at more exotic animals, or in our case, more exotic RL algorithms, here are a bunch of things that you can learn about. I really appreciate you taking the time to listen to all of this if you somehow made it here. If you spot any mistakes or you have any, thoughts that you want to share, feel free to leave them in the comments, and I'll do my best to keep this updated with any corrections. I wish you the best on your future RL journey.